Hello, fellow sapiens, and welcome to Sleepless Homo. This is your space to slow down, to let the noise of the day soften, whether you're getting ready to sleep, cooking, driving, working with headphones, or even standing in the shower. Here we tell the story of humanity softly. Careful science, humble questions, no wild speculation. If you find comfort or curiosity here, consider liking and subscribing. Not just for numbers, but because it helps others who might need this calm knowledge at 2 a.m. In the comments, I'd love to know, do you listen before bed or from some other corner of your life? Your answers shape how this channel grows, and if you drift off halfway through, I've left timestamps in the description so you can return tomorrow. The whole journey is worth it. This isn't just content, it's a conversation we're building together, across time and across sleepless nights. And as always, stay curious, stay calm. Now, did shrooms make us human? What if the first step toward becoming human began not with stone tools, but with what early hominins put in their mouths? That thought feels almost absurd, because in our textbooks the beginning of humanity is usually shown with hands striking stone, sparks flying, and the first edge being shaped against a core. But step back with me into Africa between 2.5 and 2 million years ago, when the land was a shifting mosaic of grassland, woodland, and floodplain. Imagine a group of Homo habilis, or perhaps early Homo erectus, not yet famous for fire or for grand migrations, but simply surviving one long afternoon after another. Their world is in motion. The African climate at this time is marked by cycles of wet and dry, driven by orbital shifts and distant ice building in the north. Lakes expand and contract, grasslands spread, retreat, and spread again. What this means on the ground is uncertainty. Waterholes are temporary, food is seasonal. The land demands flexibility from anyone trying to live on it. Bands of hominins walk farther each day than most creatures their size. They are scavengers, foragers, occasional hunters, and opportunists. Their stomachs are tuned to a wide diet, roots and tubers dug from the soil, seeds pounded with stone, insects pried from rotten wood, marrow cracked from bones left by larger predators. They live in the margins, picking at what the savannah allows, competing with jackals, vultures, and hyenas. In such a world, curiosity is not a luxury, it is a survival strategy. Now picture one of their ordinary routes after a storm. Rain has passed, leaving the grass damp and the soil softened. Antelope herds have moved through, leaving their signature, prints stamped into the mud and piles of dung still steaming. Around those piles, a transformation is underway. Dung is not waste in the ecological sense. It is fuel, shelter, and food. Beetles swarm over it, rolling small pellets away. Larvae hatch inside. Birds hover, waiting to snatch the beetles, and within a day or two, delicate fungi push up from the surface. Their caps are pale, fragile, and short-lived, appearing just long enough to scatter spores before collapsing back into the earth. These mushrooms, known in the modern world as dung-loving fungi, have a predictable rhythm. They follow the rains and the herds. They appear in the same places that hominins already visit, because dung is itself a signal. It points to water, to grazing animals, to possible scavenging opportunities. The overlap is unavoidable. A forager already stopping to look for beetle larvae or bone scraps would see the pale caps rising after rain. Here is where the story of the Stoned Ape Hypothesis begins. The idea is simple enough. Perhaps long before we worried about controlling fire or shaping perfect tools, some of our ancestors experimented with these mushrooms. Not once, not as an event, but as a small recurring behaviour in the flow of daily life. Not because they were seeking visions, but because they were opportunistic feeders in a landscape where passing up a potential food meant hunger tomorrow. Before we imagine too much, we should ground this carefully. We have no direct evidence that early Homo ate mushrooms of this kind. What we do have is the ecological overlap. Herbivore dung was everywhere hominins were. Mushrooms that thrive on it appear quickly after rain, in full view. Modern primates do nibble novel foods, including fungi. Chimpanzees taste and sometimes spit them out. Monkeys try small bites. Even ungulates experiment with mushrooms, which is how those fungi keep spreading. So it would be odd if early Homo, a generalist and scavenger, ignored such a visible food source entirely. The savannah 2 million years ago was not a static plain. It was a landscape of opportunities that flickered on and off like lamps. Termites swarmed on hot evenings. Fig trees dropped fruit for a week and then stood barren. A hippo carcass was a feast until hyenas stripped it, and then it was a memory. Mushrooms, brief as they were, fit into this mosaic of pulses. They were there, then gone, and the only way to benefit was to notice and act quickly. Think of the daily movement of a hominin band. They walked for hours, tracking water, following herds, scanning the ground for carcasses. Children watched their elders and copied them. The knowledge of which tubers to roast, which seeds to crack, which larvae to swallow, was passed in small gestures, not in words. If someone bent to pluck a mushroom cap and took a small bite, a child might copy. If the taste was unpleasant, the mushroom was spat out. If the effect was unusual but not immediately harmful, the memory was stored. Tomorrow, after the next rain, someone might remember that pile, that cap, that taste. Over generations, little habits accumulate. Perhaps some mushrooms were avoided because they made people sick. Perhaps others were tolerated, even sought, because they did something else. We cannot say more without drifting into speculation, but what we can say is this: the opportunity existed. The ecological setting placed mushrooms directly in the path of foragers who were already reading dung as a sign. To live in this world was to live among uncertainties. Rainfall shifted from century to century. Grasslands expanded, then contracted. Faunal communities changed, with some antelope species going extinct and new ones arriving. The fossil record from Eastern Africa shows this constant turnover. Hominins had to navigate these changes not with plans, but with flexibility. Sampling new foods was part of that flexibility. If we think of survival not as a single strategy, but as a library of small tricks, then trying a mushroom after rain was one more line on the shelf. The idea that such a line could, over time, influence how hominins interacted with their environment is what later thinkers like Terence McKenna tried to capture in the Stoned Ape Hypothesis. But in this early moment, it is not about philosophy or culture. It is simply about the landscape, the food web, and the behaviour of opportunistic foragers. Consider the role of dung itself. It was a central hub in savanna ecology. It fed beetles, which in turn fed birds. It carried seeds that germinated in its moist soil. It burned when dried, sometimes used as fuel by later pastoralists. For early Homo, dung meant opportunity. Insects to eat, animals to track, signals of herd movement. If mushrooms appeared there too, they were folded into this web of meaning. To treat dung as unclean is a modern luxury. In the savannah, it was a resource. In the evenings, when heat gave way to cooler air, the band might pause near a watercourse where herds had rested. Children poked at piles with sticks looking for beetles. Adults cracked open bones scavenged earlier in the day. Someone plucked a mushroom and tested it. It was not a ceremony, not a revelation, just one more experiment in a world that required constant experiments. This is the setting we can reconstruct with some confidence. Africa, 2 million years ago, in a time of environmental variability, with hominins who lived by their wits and their willingness to try. Whether those experiments had long-term effects on our lineage is a matter for debate. But the first strange meal, if it happened, was probably like this. Small, ordinary, and repeated often enough to become part of the pattern of life. It is humbling to think that our story may not have begun with the thunder of stone against stone, but with a quiet bite of something growing in the shadow of dung after rain. And it leaves us with a simple, enduring question. In a world where survival depended on trying almost everything, how many of those small, strange meals changed the course of who we became? To carry the picture forward, we can look at the broader cast of creatures sharing this stage. The African savannah at the turn from the Pliocene into the Pleistocene was not a quiet place. Herds of grazing animals moved in numbers that left entire valleys grazed flat within weeks. Predators shadowed them: lions, saber-toothed cats, hyenas with bone-crushing jaws. Alongside them were smaller players: warthogs rooting for bulbs, birds scanning the grass for insects, tortoises browsing slowly through patches of greenery. Each of these animals left traces that others could use. To survive in this ecosystem, you needed to be more than strong. You needed to be attentive. Early Homo fit this niche well. Their bodies tell us they were walkers, built for endurance rather than speed. Their teeth and jaws suggest a varied diet, capable of chewing tough vegetation, but also suited for scavenged meat. Archaeological sites from this horizon show flakes of stone that hint at meat processing, but far fewer traces of daily meals. Plants, insects, and other fragile foods rarely fossilise. This silence in the record tempts us to forget that the bulk of their calories probably came from things that leave no trace. And it is in this shadowy diet that the possibility of fungi sits comfortably. One of the overlooked aspects of these landscapes is the role of rainfall, not just in feeding grass but in shaping time itself. When the rains came, everything shifted. Plants greened, animals migrated, insects exploded in number. Hominins too had to adapt their paths. The rains created windows of opportunity, and mushrooms were one of the quickest responders to those windows. They did not wait weeks like trees. They appeared overnight. For a forager walking in a post-rain savanna, the world was filled with little surprises, some fleeting, some dangerous, some nourishing. Mushrooms belonged to that category of ephemeral abundance, resources that appear suddenly, reward those who act quickly, and vanish almost as fast. What makes this detail significant is not the mushroom itself, but the logic of survival it represents. Early Homo did not thrive by waiting for certainty. They thrived by gambling on novelty in measured doses. This is visible in their stone tools, which show experimentation with shapes and materials. It is visible in their wide geographic spread, which shows willingness to enter new habitats. And it is visible, we suspect, in their diets, which must have included risks and tests. To bite into a mushroom after rain was not out of character. It was exactly in character for a species surviving on uncertainty. In the end, whether those early bites carried psychoactive compounds or not, they were part of a broader rhythm. The first strange meal was not an accident, nor a plan. It was the consequence of living in a landscape where survival meant tasting the world, one small bite at a time. Why did so many human stories start in East Africa's Great Rift? It is a question that paleontologists, geologists, and biologists have circled around for more than a century, because again and again, when the bones of our ancestors appear, they so often come from this long scar across the continent. The Rift Valley is not one place but a system, stretching from the Red Sea in the north all the way to Mozambique in the south, pulling apart slowly over millions of years as tectonic forces tugged at Africa's crust. In that pulling, the earth opened great depressions, some of which filled with lakes, others with shifting wetlands, still others with grasslands bordered by cliffs and escarpments. This variety made the region not just dramatic to look at, but biologically rich. For creatures searching for food, shelter, and water, the rift was a kind of buffet line of habitats. By the time between 3 million and 2 million years ago, several hominin species were walking these landscapes. Australopithecus afarensis, famous from the skeleton known as Lucy, had been present for hundreds of thousands of years. Other forms such as Australopithecus africanus in the south, and later Paranthropus boisei in the east added diversity to the picture. These hominins were small-bodied compared to us, with ape-like faces and long arms, but their hips, knees, and ankles were adapted for upright walking. Fossils and wear marks on their teeth tell us that they were not living on one narrow menu. Instead, they expanded their diets to cope with a changing environment. It is in these adaptations that we see the story of survival unfold. The Rift Valley during this window was a dynamic place. Climate shifts oscillated between wetter and drier phases. Lakes filled and shrank, forests spread and retreated, grasslands advanced and withered. Each swing reshuffled the availability of resources. For hominins, this meant that a reliance on any single food source was risky. A diet too tied to fruit could fail when trees receded. A diet too tied to grazing animals could collapse when herds moved elsewhere. The solution was not to specialize further, but to diversify. And so Australopiths broadened their palates, taking in tougher plant matter, roots, bulbs, insects, and likely small amounts of meat when available. Evidence for this comes from isotope analysis of their tooth enamel. carbon isotopes preserve a chemical fingerprint of what sorts of plants were eaten. Plants that grow in shaded forests leave one signature, while grasses and sedges leave another. The enamel of Australopiths shows a surprising range, indicating they sampled both categories. In some individuals, almost half the diet seems to have been grass-derived foods, whether directly from sedges or indirectly from the animals that ate them. This is not the diet of a picky specialist. It is the diet of a generalist willing to test whatever the landscape offered. Among those offerings were underground storage organs, roots and tubers buried beneath the soil. These are calorie-dense packages, but they are also tough, fibrous, and often chemically defended with bitter compounds. Extracting them required both physical effort and chewing power, traits that Australopith jaws and teeth supplied in abundance. Paranthropus boidae, sometimes called the nutcracker man, had immense jaws and molars that seem adapted for just this kind of heavy-duty grinding. In the Rift Valley buffet, tubers were dependable backup rations, available even in drier phases when other foods failed. To dig them up and make them edible was a mark of resilience. Insects too played a role. Today, baboons, chimpanzees and other primates spend significant time flipping over dung or logs to capture grubs, termites or beetles. Protein-rich, seasonally abundant and often gathered in clusters, insects are a logical supplement. Though insect remains are rarely preserved, indirect evidence from wear patterns on teeth and comparisons with modern primates suggests early hominins probably exploited them. The Rift Valley's mixture of forest patches and open plains would have provided many such opportunities. And then there were fungi. They do not fossilise well, so their presence is often invisible to us. Yet mushrooms are common in grassland ecosystems, particularly in the wake of rain, and several species grow directly from animal dung. In a landscape filled with herds of grazing animals, zebras, antelopes, elephants, the byproducts of digestion littered the ground. For hominins already investigating dung piles for insects, stumbling upon fungi would have been unavoidable. Whether these mushrooms were regularly eaten is something we cannot prove, but their ecological availability is clear. Like tubers and insects, they belong to the category of opportunistic finds, foods that required curiosity to sample and experience to evaluate. This diet of variety reflects not only the resourcefulness of our ancestors, but the setting that shaped them. The Rift Valley was a crossroads of environments. Lake shores offered fish, shellfish and waterfowl. Forest margins offered fruits and nuts. Grasslands offered seeds, tubers and the occasional carcass. Wetlands offered sedges and aquatic plants. To live here was to learn not one skill but many. To memorise the seasonal calendar of foods. To carry in memory a map of where to find calories at each stage of the year. Stone tools, which appear in increasing numbers after about 2.5 million years ago, gave hominins another advantage in this ecological buffet. With sharp flakes they could cut meat from bones or slice tough roots. With hammerstones they could crack open marrow-filled bones left behind by larger predators. But even before the tools, the willingness to try different foods had already set these species apart. Flexibility, not strength, was the key adaptation. If we think of the Rift Valley as a vast shifting dining hall, then early hominins were the diners who never ordered the same dish twice. They tested tubers, insects, seeds and fungi. They scavenged meat when possible and gathered fruits when available. Each choice carried risk, poisonous plants, dangerous competition from other animals, but the broader the range, the better the odds of survival when climates swung again. So why did so many human stories start in East Africa's Great Rift? Perhaps because it was here that survival depended most on adaptability. It was here that our ancestors learned not to rely on a single food, but to explore, taste, and remember. This lesson, taught by shifting lakes and drying grasslands, would echo through all later human history. To be human, in part, was to face a buffet where the menu changed constantly, and to walk away nourished nonetheless. And in that changing buffet, strange meals were inevitable. Some were nourishing, some risky, some perhaps transformative, but all of them were steps on the long road from ape to us. One of the subtler lessons of the Rift Valley buffet is how it shaped social behaviour. When food is scattered across different niches, roots underground, insects in mounds, fruits in canopy patches, fungi after rain, it encourages foraging in groups. A lone individual might overlook a key source or waste time on a bad lead. but in groups knowledge could be pooled. One member might remember where a stand of tubers could be dug. Another might recall which termite mounds were still active. A third might notice the telltale shapes of mushrooms after a storm. In this way, diversity of foods encouraged diversity of memory and observation. It made ecological knowledge into a shared inheritance, not just an individual skill. Archaeologists sometimes call this the cognitive map of foragers, the internalized memory of landscapes and their shifting resources. In the Rift Valley, this map was constantly rewritten. Lakes rose and fell, forests advanced or retreated, herds shifted their migration paths. By walking, observing and eating, hominins updated their maps. Each successful return to a resource confirmed its reliability, while each failure sent the group searching elsewhere. These maps were not drawn on stone or bark, but held in memory and in the habits of the group. To survive, children had to learn these maps from their elders, just as primates today learn what to eat by watching others. Predators also shaped the choices available. Every carcass was a gamble. Hyenas might already be circling. Lions might return at any moment. To exploit such resources, hominins had to act quickly, cutting meat or marrow before danger arrived. This pressure may explain why opportunistic foods like insects, tubers or fungi were so important. They could be gathered without direct conflict. They were low-risk calories compared to challenging a big cat over a carcass. The Rift Valley also offered seasonal abundance that could not be ignored. Certain trees dropped nuts in great quantities. Certain grasslands yielded waves of seeds. Certain wetlands hosted mass gatherings of birds or fish. These pulses of calories may have allowed groups to grow in number or travel further, but the flip side of abundance was scarcity. When the season passed, those foods vanished. Once again, the buffet was reset, and only those with flexible diets could bridge the gap to the next feast. Even though the fossil record only preserves fragments, the broader picture is clear. The Rift Valley forced early hominins to embrace a kind of culinary curiosity. Their survival depended not on perfecting a single trick, but on stringing together many small ones, adjusting with each season, each shift of climate, each migration of animals. This buffet was not indulgence, but endurance. It was the testing ground for a species that would, eventually, leave the valley and spread across the world, carrying with them the lessons of diversity learned in its shifting landscapes. How did sweating and jogging change what we could chase, and what we might stumble across while chasing? Around 2 million years ago, a new hominin appeared on the stage of East Africa that altered the way survival was written into the body. We call it Homo erectus, the upright man, and its arrival marked one of the most significant shifts in human history. For the first time, a species of hominin evolved not just to stand and walk, but to run, slowly, steadily, and for astonishing distances. This capacity for endurance reshaped what foods could be reached, what environments could be colonized, and what kinds of encounters were possible along the way. The evidence begins with bones. Compared to their Australopith predecessors, Homo erectus had longer legs and shorter arms, proportions more like our own. Their rib cages narrowed, their pelvises became more efficient for striding, and their feet lost the grasping capabilities of tree dwellers. The arch of the foot became a spring, the Achilles tendon lengthened into a shock absorber, and the gluteal muscles grew into stabilizers for long-distance running. All of these features suggest a creature designed less for short bursts of climbing and more for sustained travel across open ground. But bones tell only part of the story. The skin tells another. While we cannot fossilize sweat glands, we can infer their importance from hair. Compared to other primates, humans are strikingly naked. This loss of dense fur, combined with a dramatic increase in eccrine sweat glands, allowed Homo erectus to shed heat while running in the midday sun. Most prey animals overheat quickly when pursued over long distances, even if they can sprint faster. A well-paced group of hunters jogging for hours could push an antelope or zebra into exhaustion, catching it not by speed but by persistence. This practice, called persistence hunting, still exists among some traditional societies today and demonstrates the power of sweat and stamina as evolutionary tools. Persistence hunting would have opened entirely new avenues of nutrition. Large carcasses provided meat and marrow, both dense sources of calories. But the running itself also expanded horizons. Chasing herds meant leaving familiar territories, tracking animals into new valleys, across rivers, and into landscapes not previously explored. Each new route exposed Homo erectus to plants, roots, insects, and fungi unknown from their home base. Endurance did not just widen their hunting range, it widened their ecological education. The jogging ape became the sampling ape. This mobility helps explain why Homo erectus fossils appear not only in East Africa, but soon after in Georgia, Indonesia, and China. Within a few 100,000 years, this species had spread across much of the Old World. Such a rapid expansion was possible only because their physiology allowed them to walk and run far, to carry knowledge and habits into novel landscapes, and to adapt to the foods they found there. The Rift Valley buffet was no longer enough. Now the menu included Asian grasslands, European woodlands, and island coastlines. Endurance travel also shifted group dynamics. Covering long distances required cooperation. Individuals had to pace themselves, share water, and divide the labour of tracking and butchering. Successful hunts demanded patience and communication of some kind, even if only through gestures and shared memory of routes. While we cannot reconstruct their conversations, we can see the traces of coordination in butchery sites, where multiple carcasses were processed, bones broken open systematically, and stone tools reused. Jogging together meant not only catching prey, but sustaining one another over the miles. Sweat and stamina also had unexpected side effects. To fuel long hunts, groups needed portable food. Dried meat, tubers carried in slings, seeds gathered en route, all these became part of a more mobile subsistence strategy. Unlike a chimpanzee band that might feast in one fruiting tree, Homo erectus lived by stringing together scattered meals, each one discovered in a different corner of the landscape. This opportunism increased the odds of stumbling across unusual foods. Fungi after rains, shellfish in coastal shallows, wild honey in hidden hives, all could be incorporated into the expanding diet. The very act of jogging into new territories made the range of edibles greater than ever before. What is remarkable is that none of these changes required abstract planning or symbolic thought. They were practical, embodied responses to the challenges of survival. A body tuned for sweat and stride created new possibilities, and those possibilities reshaped behaviour. Each hunt, each forage, each journey built on the last, creating a rhythm of life measured not just by seasons but by miles. So when we ask how Homo erectus survived, the answer is not only that they learned to run, but that running carried them into new relationships with the land. The savannah was no longer a closed circle. It was a corridor stretching outward, dotted with herds, waterholes, and food sources waiting to be discovered. Jogging was not just locomotion, it was exploration, and through exploration came both calories and curiosity. When we picture Homo erectus striding across the savannah, it is tempting to imagine them only in pursuit of game. Yet much of their running and walking may have had nothing to do with hunting at all. Moving long distances meant connecting scattered waterholes during dry spells, reaching seasonal fruit groves, or keeping up with migratory herds not to kill them, but to shadow them and scavenge the leftovers from larger predators. In this way, their new endurance was not just about the thrill of the chase, but the quiet practicality of covering the ground required to keep a group alive in fluctuating climates. These movements also brought them into landscapes their predecessors had barely touched. Volcanic highlands, coastal plains, deep river valleys all became part of their territory. Each setting presented its own challenges and its own rewards. In volcanic soils, roots and tubers grew thick, providing dependable calories. Along rivers, fish and aquatic plants supplemented the diet. On coastlines, shellfish and stranded carcasses could be gathered. Endurance gave Homo erectus the freedom to sample each environment and carry lessons back to the group. What had once been a narrow ecological niche widened into a patchwork of survival strategies. With broader ranges came exposure to new dangers. Pathogens in unfamiliar water sources, predators not encountered before, even plants with toxins their ancestors had never sampled. All were risks of expansion. The ability to sweat and jog kept the body moving, but it did not provide immunity to these threats. To navigate them, Erectus likely relied on trial and error, observation, and the cautious adoption of habits. Watching what other animals ate, testing small bites, and remembering the outcomes would have been vital. Mobility gave them options, but it also demanded careful attention to avoid mistakes that could cost lives. Another subtle consequence of long-distance travel was the reshaping of time. For Australopiths, the rhythm of life may have been set by daily foraging routes within a limited home range. For Homo erectus, time stretched into journeys measured by days and weeks. A hunt might lead a group tens of kilometres from their base. A migration shadowing herds might carry them across an entire valley. This expansion of temporal horizons changed how they interacted with their world. They were no longer simply harvesting what was nearby. They were planning, even if in a rudimentary way, for what might be encountered further on. In the end, the gift of running was less about speed than about persistence. It allowed Homo erectus to persist in pursuit, persist in exploration, persist in adapting to each new environment they entered. And persistence, more than any single innovation, may have been the trait that made them one of the most successful hominin species in history. In the long arc of human history, 2 million years ago marks the point where survival became a matter of endurance. And endurance meant more than chasing prey. It meant enduring the unknown, stepping into unfamiliar territories, and trusting that the body, the group, and the land together would provide enough to go on. That gamble, repeated over countless hunts and migrations, may be what carried our ancestors out of Africa and into the wider world. What was growing in the dung of those vast grazing herds? To answer that, we have to imagine the East African savannah as it existed between 2 million and 1.8 million years ago. This was not a static plain, but a living machine, driven by migrations that moved like tides across the land. Wildebeest, zebra, antelope, elephant and other herbivores grazed down the grasses and then drifted onward in search of fresh shoots, leaving behind a trail of droppings that transformed the ground they crossed. In those heaps of waste, life found a second chance. Beetles rolled balls to bury their eggs, flies laid larvae, and hidden threads of fungi began to fruit. Among the fungi, some belonged to the genus psilocybe, organisms adapted specifically to dung-rich environments. Their life cycle was simple yet opportunistic. Spores, microscopic and hardy, drifted on the wind or passed unharmed through the digestive tracts of animals. When they landed on moist dung, they germinated, feeding on the rich organic material and producing networks of filaments. When the conditions were right, after a good rain, when humidity rose, they sprouted fruiting bodies. To the casual eye, these mushrooms were just another small form of growth on the grassland floor. But ecologically, they were opportunists, quick to seize the nutrients provided by herds, and just as quick to vanish when the sun baked the ground dry again. What makes this pattern interesting is its scale. Herbivore herds in the early Pleistocene were immense. Fossil pollen, bones, and trackways all suggest that East Africa supported animal populations at least as dense as those still found in modern Serengeti reserves. Each herd was a moving factory of dung, dropping countless opportunities for fungi to flourish. As animals travelled, they transported spores in their guts and on their hides, seeding new pastures with the ingredients for fungal growth. In effect, the animals were gardeners of the savannah without knowing it, maintaining an unending crop of mushrooms that followed their movements. Hominins living in these landscapes would have been drawn to dung for many reasons, long before they ever noticed mushrooms. Dung piles attracted beetle grubs and fly larvae, small but protein-rich meals. They marked the presence of herds, helping hunters and scavengers track animals. They fertilized the grasses, creating patches of new growth that could lure grazers back. To flip over dung in search of insects was already part of the behavioural repertoire of baboons and chimpanzees, and it is likely our ancestors shared this habit. In that context, encountering mushrooms was nearly inevitable. The appearance of mushrooms after rain would have been especially striking. When the sky cleared and the land glistened with moisture, new growths emerged overnight. To a forager scanning for edible shoots or insects, these sudden fruits would have stood out. Some species were bland, some bitter, some toxic. Sorting them required experience, trial, and error. But in a world where nearly every plant or fungus could be a candidate for food, curiosity was rewarded as often as it was punished. For a hominin walking the herd paths of the Rift Valley, mushrooms were one more item on a long list of possibilities. It is important to emphasize that these mushrooms were not rare. They were woven into the ecology of grazing systems. Dung is one of the most nutrient-rich substrates in a grassland, and fungi were among its most successful recyclers. The spores of psilocybin and related genera are extraordinarily resilient, surviving desiccation and sunlight, and germinating rapidly when the rains returned. In ecological terms, they behaved like weeds of the fungal kingdom, quick to appear, quick to reproduce, and dependent on disturbance, in this case, the constant trampling and grazing of herbivore herds. What we know from modern analogues suggests that Homo erectus, or late Australopiths, would have encountered these fungi routinely. Whether they chose to eat them is harder to say. Some mushrooms were edible and nutritious, others dangerously toxic. Ethnographic studies of modern foragers show a wide range of strategies for dealing with fungi, from enthusiastic consumption to cautious avoidance. Without written records, we cannot know the choices made 2 million years ago. But the ecological availability is not in question. The savannah's hidden crop was always there, seeded by herds, watered by rains, and sprouting in cycles that matched the rhythms of the land. This relationship between grazing animals and fungi hints at a larger pattern, the interconnectedness of species. Hominins relied on herbivores for meat and scavenging opportunities, but herbivores also created indirect food webs that supported insects, birds, and fungi, all of which became potential meals for clever foragers. By following herds, Homo erectus was not simply chasing prey. They were plugging into an entire ecological engine that generated calories in many different forms. Each pile of dung was more than waste. It was a microcosm of opportunities, a patch where the soil turned briefly into a banquet. So what was growing in the dung of those vast grazing herds? A cycle of life invisible at first glance but vital to the balance of the savannah. Spores waiting for rain, fungi waiting for spores, hominins waiting for their chance. Whether or not our ancestors made a habit of eating these mushrooms, the fact remains that they lived in a world where such encounters were unavoidable. The hidden crop of the savannah was a quiet constant in their environment, one more thread in the dense web of survival that stretched across the grasslands of Africa. Another way to think about the savannah's hidden crop is to picture it as part of a recycling chain. The herds consumed vast quantities of grass, stripping whole plains within weeks. What they digested was not wasted. Their droppings returned concentrated nutrients to the soil, nitrogen, phosphorus, and carbon, ready to be broken down. Beetles carried pieces underground, flies deposited eggs, and fungi spread their invisible threads through the piles. The mushrooms that appeared were only the visible tips of much larger underground networks, hidden mats of mycelium that stitched together the ecology of the grassland. In this sense, mushrooms were less a rare treat than an essential cog in keeping the system alive, turning waste back into fertility. For hominins moving among these processes, the fungi were silent companions. They did not roar like lions or stampede like antelope. They emerged quietly, often in circles or clusters, offering flashes of texture against the flattened grasses. To a hungry group pausing near a herd's trail, the appearance of mushrooms might have been taken as a simple bonus, a chance to supplement a meal of roots or insects. Even if their nutritional contribution was minor compared to meat or tubers, they were part of the suite of foods that kept foragers from relying on any single source. Modern studies of mushroom ecology in East African pastures suggest that these fungi appear most consistently in areas where animals graze heavily, but the soil remains moist. In the early Pleistocene, this would have meant areas along lake shores, wetlands, or recently rained-upon valleys, exactly the kinds of places Homo erectus was likely to explore. The timing of their growth, following rains, also lined up with moments when plant foods were flush and animal movements unpredictable. Mushrooms were part of the seasonal rhythm, a food that required attention to timing and memory. This is not to say our ancestors cultivated fungi or treated them as a staple. Instead, they probably fit into the opportunistic logic of foraging. If it looks edible, try a little. If it proves useful, remember the conditions and return next season. In that way, mushrooms joined berries, tubers, fish, insects, and carcasses in the growing catalogue of resources Homo erectus carried in mind. Survival in such landscapes was not about mastery of one crop or one prey animal, but about holding a wide repertoire of possibilities and knowing when to use each. When we picture the Rift Valley and its grasslands 2 million years ago, we tend to focus on the dramatic. Hunters chasing prey, predators clashing, herds on the move. Yet beneath this spectacle lay the quiet contributions of organisms like fungi. They shaped soil fertility, provided passing nourishment, and served as reminders that not all food comes from the chase. Some food simply waits for the rain and rises from the ground, offered without struggle to those attentive enough to notice. What if the thing that set our ancestors apart was not just their ability to hunt or to cook, but their willingness to taste what others would have avoided? Curiosity has always been a double-edged trait in primates. It pushes individuals toward new food sources, sometimes yielding crucial discoveries, but it also risks exposure to poisons, parasites, or predators. In the African landscapes of the early Pleistocene, where Homo erectus and their relatives roamed, every mouthful could be a gamble. Tubers had to be tested for bitterness, berries for sweetness, carcasses for freshness, and fungi for edibility. Why would a hominin reach for a mushroom that seemed strange, brightly coloured, or simply out of the ordinary? Because in primates, experimentation is not an accident, it is part of survival. We see this today in our closest relatives. Chimpanzees sample fermented fruits that contain small amounts of ethanol, not always stopping when the fruit has gone beyond the stage most animals tolerate. In some studies, wild chimpanzees have been observed deliberately seeking out palm wine left fermenting in tree hollows, dipping leaves into the liquid and sipping with a clear sense of enjoyment. Baboons are known to raid vineyards in modern agricultural zones, sometimes consuming enough alcohol from ripe or fermenting grapes to appear intoxicated. These behaviours are not driven by nutritional necessity. They are playful, exploratory, and sometimes reckless, yet they reveal a deep continuity in the primate tendency to test the boundaries of edibility. Other examples stretch beyond alcohol. Dolphins have been filmed gently passing around pufferfish, nibbling at them just enough to release neurotoxins in low doses. Afterward, they seem to enter trance-like states, floating together near the surface. Jaguars in the Amazon chew the bark and leaves of hallucinogenic plants, rolling on the ground afterward in a manner that suggests disorientation. Even elephants are rumoured to seek out fermented marula fruit in southern Africa. Though whether this is myth or occasional truth, the story persists because it fits the larger pattern. Animals sometimes pursue experiences that alter their perception of the world. For early hominins, this curiosity may not have been about pleasure alone. To a forager in a world of scarcity, new foods always had potential value. Mushrooms in particular represented a curious case. Some were rich in protein and minerals, others dangerously toxic. There was no visual code that guaranteed safety, and learning which was which required either costly mistakes or careful observation of animals. Watching ungulates graze around certain mushrooms without ill effect could encourage sampling. Seeing others avoid them could provoke hesitation. Yet among primates, hesitation is rarely universal. Some individuals push forward, nibbling, sniffing, and testing. Their risks create knowledge for the group. This experimental streak may have served as insurance in volatile environments. During dry seasons or after poor hunts, novelty could mean survival. An ape brave enough, or foolish enough, to test an unusual food might stumble upon an overlooked source of calories. Even if a mushroom offered little in the way of sustenance, the act of testing reinforced a pattern of openness, a willingness to try the unfamiliar. This attitude would later prove critical as hominins expanded across continents, encountering new climates, plants, and animals. A lineage that shied away from experimentation might have survived in stable forests, but not on the shifting savannahs of Africa or the unpredictable steppes of Eurasia. Of course, curiosity had its costs. Some mushrooms can cause stomach distress, others seizures, and a few, death. It is unlikely that groups escape these dangers entirely. Yet just as modern primates sometimes accept discomfort for the sake of exploration, so too might hominins have tolerated occasional setbacks in exchange for the broader benefit of dietary expansion. Evolution does not favour safety alone. It balances risk against reward, and curiosity is one of its boldest bets. The question is not whether hominins ate strange foods. They clearly did, but how far their curiosity went. Did they, like chimpanzees and dolphins, notice the altered states that followed and returned for more? Or was it enough to nibble once and move on, chalking the experience up to misadventure? We cannot know with certainty, but the continuity across the animal kingdom suggests that the temptation to revisit an unusual sensation is not unique to us. In that light, the first ape who reached for a mushroom growing in the shadow of dung was not simply hungry. They were participating in a lineage-wide experiment, one that every primate continues in some way today. What remains striking is that this experiment was never entirely rational. It was playful, instinctual, and shaped by chance. Yet from such chance encounters, habits form, and from habits, cultures emerge. If animals as different as dolphins, jaguars, and chimpanzees occasionally pursue intoxication, then perhaps curiosity itself is the hidden crop of evolution, always ripening, always tempting, and always reminding us that risk and discovery are inseparable companions. Another angle to consider is how hominins may have learned indirectly, not only from animals but from each other. In small groups, one individual's mistake, or lucky discovery, became a shared lesson. If someone became ill after eating a certain mushroom, others could avoid it. If someone behaved oddly but not fatally after consuming another, the group might have remembered both the incident and the conditions that led to it. Oral traditions did not exist yet, but memory, imitation, and observational learning are ancient primate tools. A strange meal could become a marker, that plant near the termite mound, or those caps that appear after rain. Such notes in the mental map of the landscape added to the shared survival guide every band carried in their heads. Curiosity also thrived in the hands of juveniles. Young primates today are notorious for tasting, poking, and prodding far more than their cautious elders. Chimpanzee infants put leaves in their mouths, play with insects, and investigate plants that adults ignore. This pattern may have existed among early hominins too. The younger members of the group, shielded somewhat by the vigilance of adults, could test the edges of the edible world. Their experiments may have sometimes ended badly, but they also expanded the group's knowledge. A mushroom first nibbled by a reckless juvenile might later be remembered as either a hidden food or a warning sign. The social dynamics of sampling are important too. Food sharing among early hominins is suggested by cut marks on bones and traces of butchery. If meat was distributed, so too might smaller finds like tubers or fungi have been passed around. What began as one person's discovery could quickly ripple through the band, turning a single bite into a group experience. Even if most individuals were cautious, the influence of one bold explorer could expose many to something new, and once the pattern was established, once the group learned that these mushrooms don't kill you, they might have looked for them again in the same season. It is also worth noting that human taste receptors are unusually broad. Compared with many mammals, we are sensitive to a wide range of bitter, sour, and umami compounds. Some researchers suggest this helped early hominins evaluate plant foods and avoid toxins, but it also meant that new foods could offer surprising sensory rewards. The sharp tang of fermented fruit or the earthy flavour of fungi may have stood out against the relatively bland palate of roots and grass seeds. Curiosity was not only about risk, it was also about pleasure. Taste itself can reinforce behaviour, encouraging repetition of whatever feels rewarding, even if the nutritional value is modest. Put together, these threads suggest that curiosity was not a marginal quirk, but a central survival strategy. By sampling, watching, sharing, and remembering, hominins expanded the menu available to them in unpredictable environments. Some of those experiments surely ended in discomfort, but others carved new paths of possibility. In that delicate balance of risk and reward, the line between survival strategy and playfulness blurred. What looks like folly from a distance may have been, in practice, one of the most enduring strengths of our lineage, the courage to put something unfamiliar in the mouth and to see what happened next. Could one mushroom really rewrite the story of evolution? That is the question Terence McKenna posed in the 1970s, when he first began sharing what would later be called the Stoned Ape Hypothesis. To him, the story of Homo sapiens was incomplete without fungi, and not just any fungi, but the ones that could change perception, mood, and self-awareness. It was not enough to say that humans became human because they picked up stones, crafted spears, or learned to cook. McKenna asked us to imagine that the spark of humanity began with something smaller, stranger and easily overlooked, a mushroom sprouting from the dung of grazing animals. McKenna's framing was both simple and radical. He divided the mushroom experience into 3 levels, each of which he believed could have shaped human evolution. At the lowest dose, he argued, psilocybin improved visual acuity. Edges sharpened, movement stood out, and the subtle contrasts of grass and shadow became easier to pass. For a hominin on the savannah, this meant practical advantages: spotting predators earlier, tracking prey more efficiently, and navigating landscapes with a keener sense of detail. A mushroom, in this view, was not just a curiosity but a survival tool hidden in plain sight. At medium doses, McKenna believed the mushroom influenced sexuality and sociability. It heightened arousal, increased energy, and made individuals more likely to seek contact. If true, then mushroom eaters might have reproduced more successfully, passing on their genes and gradually shifting the population toward traits reinforced by this altered behaviour. More mates, more children, more descendants who carried the lineage forward. The mushroom, once again, would be more than an incidental snack. It would be a quiet architect of demographic momentum. At the highest doses, McKenna claimed, psilocybin dissolved the ego. Individuals no longer felt isolated but merged with the group, with the landscape, and even with imagined entities beyond themselves. This, he suggested, gave rise to ritual, religion, and the first glimpses of symbolic thought. Small bands gathered together under the influence might have sung, danced, or shared visions that transcended ordinary communication. For McKenna, these experiences planted the seeds of art, myth, and language. The mushroom in this sense was not just a catalyst for survival or reproduction, but the doorway to culture itself. It is worth remembering the moment when McKenna proposed this idea. The 1970s were a time of renewed interest in psychedelics, long before today's scientific renaissance but still shaped by the echoes of the counterculture. His writings in Food of the Gods blended anthropology, ethnobotany, and speculation into a narrative that was less about presenting final proof than about opening a new angle of inquiry. He knew the fossil record could not confirm mushroom use 2 million years ago, yet he insisted that ignoring the possibility meant missing a potentially crucial piece of the human puzzle. The leap McKenna asked readers to make was not a small one. It required imagining that our species' defining traits, vision, sexuality, spirituality, could have been nudged along by encounters with a fungus that had no plan, no intention, and no permanence. He suggested that human evolution was not only a matter of bones and tools, but of altered states and fleeting experiences, repeated often enough to leave lasting marks on culture and biology. Whether one found this persuasive or fanciful, it reframed the way many people thought about what it means to be human. For McKenna, the Stoned Ape Hypothesis was not only a scientific speculation, but also a kind of myth-making. It offered a story in which curiosity, chance, and communion with the natural world gave rise to intelligence and imagination. He invited us to think less about straight lines of progress and more about strange detours, where the act of sampling something unexpected could ripple across millennia. If the story sounds improbable, that was part of its power. It forced the question: how much of our humanity came from the steady grind of adaptation, and how much from the accidents of appetite and play? McKenna never claimed to have the last word. He admitted that his hypothesis lacked direct evidence, and that it belonged as much to philosophy as to anthropology. Yet he also insisted that we should not dismiss the possibility just because it was difficult to prove. After all, many aspects of human origins remain mysterious, and history often hides in places we least expect. A mushroom in the grass may not seem like a world changer, but then again, neither did a chipped stone before someone struck it against another. McKenna also tried to anchor his leap in observations from modern science, although he often stretched them beyond their original scope. He drew inspiration from mid-20th century experiments that examined how hallucinogens altered human perception, seizing on any hint that vision or awareness might be sharpened under the influence. He imagined our ancestors stumbling upon these effects in the most practical settings, while tracking gazelle across tall grass, or while keeping watch at dusk. Even if his interpretation leaned more poetic than empirical, the way he wove it into a story captured imaginations far outside the walls of academia. It was not a sterile hypothesis. It was a narrative in which small details of daily life, food, sex, ritual, spiraled into the very architecture of humanity. In his lectures, McKenna often emphasized the communal dimension of mushroom use. He pictured not solitary figures wandering the plains, but groups who experimented together. For him, this was critical. Altered states did not just change individuals, they reshaped bonds, shared visions, ecstatic dances, collective awe. These could have welded bands more tightly together, easing tensions and reinforcing cooperation. Whether or not this was true in prehistory, the suggestion reframed the idea of human origins from one of competition and struggle to one where joy and communion had evolutionary weight. It was a reversal of the grim narratives of survival of the fittest that dominated earlier anthropology. He also linked his ideas to cross-cultural patterns. McKenna was fascinated by the persistence of shamanism, by the way psychedelic plants and fungi appeared again and again in indigenous traditions across continents. To him, this was not coincidence, but continuity. If later societies had used mushrooms as portals to myth and spirit, perhaps the very first societies had done something similar on a smaller formative scale. The ethnographic present became, in his telling, a mirror of the deep past. This blending of anthropology with speculation blurred lines, but it also made his case resonate with those seeking deeper origins for human spirituality. McKenna's leap has endured not only because of its claims, but because of its style. He spoke with a mix of conviction and wonder, treating the audience less as students than as fellow travellers in a shared mystery. He admitted the evidence was thin, but he framed that thinness as an invitation, not a flaw. In his view, evolution was not a dry ledger of fossils, but a living puzzle where hidden agents, plants, fungi, and chance encounters might have left subtle fingerprints. Even those who doubted his specifics found themselves drawn into the broader suggestion that human origins may have been shaped by forces stranger and more intimate than we usually allow. By proposing his mushroom-driven vision of the past, McKenna challenged us to widen the scope of possibility. Even if his hypothesis ultimately proves wrong, it serves as a reminder that the path to becoming human may have included detours, accidents, and experiments that left their mark in ways we are only beginning to imagine. Did psychedelics make hunters see sharper, or just stranger? That was the seed of one of Terence McKenna's boldest claims, and it hinged on how a handful of experiments from the 1960s were interpreted. The research he leaned on most heavily came from Roland Fisher, a pharmacologist and psychiatrist who was fascinated by how altered states changed human perception. Fisher and his colleagues were not testing early humans on the African savannah, of course. They were giving carefully measured doses of psilocybin and other hallucinogens to modern volunteers, then tracking what happened to their vision, balance, and sense of space. The question was never hunting advantage. It was about mapping how the mind reshaped itself under chemical influence. McKenna's reading of those results, however, turned them into evolutionary speculation. He suggested that psilocybin sharpened vision, specifically edge detection. In his telling, the drug acted like an optical upgrade, allowing our ancestors to spot prey more quickly, track subtle movements in the grass, and avoid ambush by predators. This was a neat story. Eat a mushroom, see the world more clearly, survive more often. But when we step back to what Fisher's experiments actually measured, the picture is much more complicated. Fisher's volunteers reported shifts in depth perception, distortions in spatial orientation, and unusual intensification of colours and shapes. Straight lines bent, objects appeared closer or farther than they were, and the edges of the visual field sometimes shimmered or vibrated. These are not the kinds of changes that make you a better hunter. They might make the world more vivid, perhaps even more interesting, but vividness is not the same as clarity. The data simply do not show that psilocybin improved acuity in the way McKenna claimed. If anything, the consistent outcome was strangeness, an altered, but not necessarily more accurate way of seeing. Modern studies have deepened this point. Neuroimaging suggests that psychedelics relax the brain's filtering systems, allowing information that would normally be pruned out to flood into awareness. This can create a sense of hyper-detail, where every blade of grass seems to shimmer with importance. But too much information can overwhelm as easily as it can help. A hunter distracted by every flicker in the savannah might not track the antelope more effectively. They might become lost in the noise of perception, unable to tell signal from background. This does not mean psilocybin was useless. It just means its effects cannot be reduced to a simple story of sharper eyes. And yet McKenna's framing persists, in part because it resonates with subjective reports. Many people who have taken psychedelics describe a sense of heightened clarity, of finally seeing the world as it really is. The colours are brighter, the patterns more meaningful, the outlines sharper. In the moment, that experience can feel profoundly true. But what feels true to the user and what provides a survival advantage are not the same. That tension between subjective certainty and objective evidence is at the heart of this debate. It is possible that McKenna was less interested in strict accuracy than in the metaphorical power of the claim. By saying mushrooms made us see better, he gestured toward a broader idea, that they changed the way we paid attention. Even if the world was distorted, it was also charged with new salience, and that shift in salience could have influenced behaviour in unpredictable ways. Did it help survival? We do not know. But it certainly complicated the way we think about the boundary between perception and reality. When we return to the early savannah, it is humbling to realise how little certainty we have. Did Homo erectus really nibble mushrooms while scanning the horizon for lions? Did psilocybin give them an edge, or did it make them stumble? The evidence we have comes not from fossils but from lab notes written millions of years later. It is a shaky foundation for rewriting the story of evolution, and yet it is precisely that tension, the space between possibility and proof, that keeps the hypothesis alive. Another way to approach this question is to ask how altered vision fits into the broader ecology of perception. Every animal filters the world differently. Eagles see ultraviolet traces on the ground left by prey. Snakes sense infrared heat signatures. Bats map space with sonar. Humans are unusual in that our visual system privileges detail and distance, a style of sight that suits open landscapes like the Rift Valley savannahs. Into this already specialised perceptual system, psychedelics introduced a radical twist. They did not give us a new sensory channel, but instead disrupted the familiar one, bending and stretching it in ways that could be thrilling, disorienting, or both. The fact that people often describe increased pattern recognition under psychedelics may also be relevant. Grasses in the savannah ripple in repetitive waves. The coats of antelope flicker with camouflage-like markings. A brain temporarily tuned to find patterns everywhere might latch onto these textures differently. Whether that would help track a moving herd or instead create illusions of movement where there was none remains an open question. Fisher's studies hint at both possibilities, with some subjects reporting sharper focus on target images, while others described confusing afterimages and trailing effects. This duality mirrors the uncertainty in applying the findings to ancient hominins. We also need to remember that vision is not just about hunting or survival. It is about how a species engages with its surroundings. An altered visual state might have led early humans to notice overlooked aspects of their environment. Colours of ripening fruits, subtle tracks in the soil, the shimmer of insects at dusk. None of these observations require perfect clarity. They only require a mind willing to linger on details it would normally ignore. In that sense, psychedelics might not have made eyesight better, but instead broadened the range of what counted as worth seeing. There is another angle too, one that Fisher himself emphasised. He pointed out that visual distortions under psychedelics were tightly linked to changes in mood and bodily awareness. When someone felt anxious, the world seemed threatening. When they felt calm, it seemed luminous. If the same were true in ancient contexts, then mushrooms may have altered not just perception, but also the emotional colouring of perception. Seeing the savannah in shades of heightened beauty or danger could have shifted how our ancestors acted within it, even if their raw ability to spot prey stayed the same. So when we ask whether psychedelics gave hunters sharper eyes or stranger eyes, the answer may be both, or neither. What they certainly did was remind us that perception is never neutral. It is filtered, biased, and bound up with the state of the body and mind. The Stoned Ape Hypothesis may overstate the survival advantages, but it also gestures toward a deeper truth, that what we see is not simply given by the world, but co-created by the chemistry of our own brains. Why did the human brain double and then double again? That is one of the most stubborn questions in paleoanthropology, and it is a story written not in sudden leaps, but in the long arithmetic of deep time. Around 2.5 million years ago, the lineage we call Australopithecus was still present in Africa. Their brains averaged about 400 to 550 cubic centimetres, a size that overlaps with modern chimpanzees. They walked upright and had freed hands for carrying tools, but their mental hardware was still limited by evolutionary standards. Something began to change with Homo habilis, a species first identified from fossils found in Olduvai Gorge, Tanzania. Habilis cranial capacity expanded to between about 500 and 775 cubic centimetres, a noticeable increase but still far from modern human levels. These early members of our genus were already experimenting with stone tools, chipping sharp flakes from cobbles to cut meat or scrape hides. The connection between bigger brains and new behaviours was evident, though whether the tools drove the brain or the brain drove the tools is a debate that remains unresolved. By about 2 million years ago, Homo erectus appeared, and with it, one of the great turning points in human history. Fossils from Africa, Georgia, China, and Indonesia all show a consistent trend toward cranial sizes averaging 1,000 cubic centimetres or more. Erectus was the first hominin to leave Africa permanently, spreading across Eurasia, adapting to varied climates, and developing Acheulean hand axes that required more foresight and planning than earlier choppers. Their brain case was elongated, with thicker brow ridges than ours, but the sheer volume placed them on a new evolutionary trajectory. The global distribution of Erectus fossils highlights that this increase in brain size was not a local anomaly, but a species-wide shift. Something in the ecological or social pressures of the early Pleistocene made larger brains advantageous, even though they carried costs in energy and childbirth risk. Over the next million years, the trend continued. Populations of Homo heidelbergensis in Africa and Europe, considered possible ancestors to both Homo sapiens and Neanderthals, exhibited brain sizes in the range of 1,200 to 1,400 cubic centimetres. By 300,000 years ago, both Neanderthals and early Homo sapiens had brains reaching, and often surpassing 1,500 cubic centimetres. In fact, Neanderthals on average had slightly larger brains than modern humans, though with different shapes emphasising the back of the skull. The doubling and redoubling of brain volume over this time span is one of the clearest patterns in our evolutionary record. But the causes remain murky. Climate fluctuations are one candidate, with expanding grasslands, shifting rainfall, and cooling ice age cycles forcing populations to adapt to unpredictable resources. Dietary changes, including increased meat consumption and possibly cooking, may have provided the calories needed to support larger brains. Social complexity, with larger groups requiring more memory, cooperation, and competition, is another factor. None of these explanations is complete on its own, and it is likely that multiple forces acted together over hundreds of thousands of years. The puzzle is sharpened by comparison with other mammals. Elephants, whales, and dolphins also developed large brains, but their evolutionary pathways differed. Even within primates, the human jump is unusual. Chimpanzees and gorillas have remained within a narrow cranial capacity range despite facing some of the same ecological challenges. Why our lineage crossed that threshold and others did not is the enduring mystery. When we lay out the fossil sequence, from the modest skulls of Australopiths to the vaulting domes of late Homo, the pattern is undeniable. The human brain expanded not in a single burst, but in a series of steps, each one building on the last. And every increase required some trade-off in energy, reproduction, and survival. The question is not just why the brain grew, but why it kept growing, long after reaching sizes sufficient for tool-making or migration. What problem was such a vast organ solving, and was the solution unique to us? Another aspect to consider in this steady swelling of the brain is the cost it imposed on the body. A larger brain is not free. It is one of the most metabolically expensive organs in the animal kingdom. In humans today, it consumes about 20% of our resting energy budget, a staggering share compared to most mammals. For early Homo, this meant every jump in brain size had to be matched by an adjustment elsewhere. Some anthropologists point to changes in the gut. Shorter intestines and smaller digestive tracts may have reduced the energy demand of digestion, freeing up calories to feed neurons. This is the foundation of the expensive tissue hypothesis. which argues that high-quality foods such as meat and marrow offset the cost of neural tissue. Others argue that the story is not quite so direct, but the general point remains. The brain grew only because the body found ways to pay for it. Fossils also reveal that these bigger brains came with risks. Wider skulls meant more difficult childbirth, a challenge that shaped the physiology of mothers and the vulnerability of infants. Compared to other primates, human babies are born unusually early and underdeveloped, their brains still growing rapidly outside the womb. This created long periods of dependency and a need for cooperative care. It is possible that the brain did not simply grow because it was useful, but because the social systems that emerged around raising helpless young made larger brains sustainable. If so, then brain expansion was as much a cultural adaptation as it was a biological one. Looking across continents, the pattern is remarkably consistent. Skulls from Java and China show Homo erectus maintaining large brain sizes for nearly 2 million years, adapting to tropical forests, temperate plains and volcanic islands. In Europe, fossils from sites such as Atapuerca in Spain reveal heidelbergensis populations with crania approaching modern volumes. In Africa, the fossils at Jebel Irhoud, dated to about 300,000 years ago, demonstrate that early Homo sapiens already possessed large brains, though shaped differently than ours today. Despite geographical separation, all of these populations converged on the same solution: more brain tissue. This convergence suggests that the pressures driving expansion were not local quirks, but global, recurring challenges faced by the genus Homo wherever it spread. And yet the story is not a simple straight line. There were pauses, even reversals. Some populations of late Homo erectus retained smaller cranial sizes. Other lineages, such as Homo floresiensis on the island of Flores, underwent dramatic dwarfing, with brains shrinking to volumes closer to Australopiths. These exceptions remind us that evolution does not have a single direction, and that the brain's expansion was always contingent on ecological and demographic circumstances. What held steady was not inevitability, but a persistent tendency for our lineage to push against limits, to explore the edge of what a mammalian brain could become. The fact that this enlargement spanned millions of years raises a final puzzle. What threshold was being chased? Why was a brain of 700 cubic centimeters not enough? Why not stop at 1,000? Why did both Neanderthals and sapiens reach volumes that no other primate line ever approached? The fossil record gives us measurements but not motives. We can plot curves, but the reasons behind them remain elusive. It is this tension between the clarity of the numbers and the opacity of their cause that makes the question of our growing brains one of the most haunting in human origins research. Was it fire-roasted meat or mushrooms that fed the brain? When scientists look at the extraordinary expansion of the human brain between 2 million and 500,000 years ago, they do not find a single cause but a landscape of competing hypotheses. At the centre of this puzzle is energy. A larger brain demands more fuel, and somewhere along the way our ancestors stumbled upon strategies that delivered enough calories to sustain such a costly organ. The most famous of these is the cooking hypothesis, proposed by Richard Wrangham. According to this model, the mastery of fire allowed early Homo to unlock calories from meat and plants more efficiently than chewing them raw. Roasted tubers and simmered marrow required less energy to digest and released more nutrients. By this logic, fire acted as an external stomach, shrinking our guts and redirecting resources to our skulls. The fossil record provides indirect hints of this shift. Smaller jaws and teeth in Homo erectus compared to Australopiths, a reduced rib cage suggesting a shorter gut, and archaeological traces of burned bones and ash deposits in caves around 1 million years ago. Yet the exact timing of habitual fire use remains debated, with some researchers skeptical that it became widespread early enough to explain the initial surge in brain size. Another contender is the social brain hypothesis, which shifts the explanation from food to relationships. Robin Dunbar and others have argued that the demands of living in increasingly large and complex groups selected for bigger brains capable of managing alliances, rivalries, and communication. Here the brain is not an energy storage solution, but a survival strategy for social mammals navigating volatile networks. This idea gained some traction from correlations across primates. Species with larger groups tend to have bigger neocortices. Still, correlations do not prove causation, and critics note that early Homo lived in relatively small bands by modern standards. Whether social juggling alone could drive brains to triple in size is far from settled. The simplest explanation, sometimes called the expensive tissue or calorie surplus model, looks at meat itself. Scavenging and later active hunting delivered dense calories in the form of fat and protein, allowing hominins to escape the limits of plant-based diets. Stone tools found alongside butchered bones show that our ancestors were processing carcasses as early as 2.5 million years ago. With every rib cage cracked open for marrow and every skull split for brains, calories once locked inside savanna herbivores flowed into hominin bodies. It is plausible that this surplus powered gradual brain enlargement, particularly when combined with cooperative food sharing, but this model too leaves gaps. Other carnivores had access to meat, yet none experienced the same neural expansion. Something else must have been at play. Into this crowded field, the Stoned Ape Hypothesis positions psychedelics not as the sole driver, but as one of many possible ingredients. Terence McKenna argued that psilocybin mushrooms could have offered perceptual benefits, social bonding effects, and moments of creative insight that nudged evolution along. Whether one accepts his framing or not, the point remains that chemical encounters with the environment were part of the evolutionary buffet. Just as roasted tubers, fatty marrow and cooked meat shape the metabolic foundation of the brain, psychoactive plants and fungi might have influenced the behavioural niches within which that brain operated. The evidence for this is sparse, speculative and controversial, but the broader lesson is that no single food or practice explains the whole story. By the time Homo heidelbergensis walked the earth around 500,000 years ago, brains had already doubled from habilis levels. Fire was certainly in use, though how regularly remains debated. Social groups had grown in complexity, with hints of hunting cooperation and large-game butchery. And somewhere in the mix, as the savannahs pulsed with herds and dung-sprouted fungi, the possibility of chemical encounters lingered. The evolutionary record tells us only that brains grew. It cannot tell us which combination of calories and chemicals tipped the balance. What it does remind us is that the path to modern humans was not linear but layered, built from diets, tools, fires, and perhaps even fungi, each one adding weight to the scale of survival. Another lens on this question is how these different hypotheses interact rather than compete. It is easy to imagine cooking, meat sharing, and social pressures as separate drivers, but in reality they likely reinforced each other. A group that gathered around fire not only gained softer calories but also a place for coordination and exchange. Firelight extended the day, turning evenings into opportunities for planning hunts, teaching skills, or resolving disputes. That extra social time may have intensified the very dynamics the social brain hypothesis emphasizes. Likewise, cooperative hunting did not just deliver meat. It demanded communication, role assignment, and trust, all of which placed new demands on cognition. In this sense, calories and cooperation were two sides of the same coin. Energy was needed to fuel bigger brains, and bigger brains were needed to secure energy through coordinated strategies. Comparative studies in modern hunter-gatherer societies shed some indirect light. Ethnographers note that success in these groups is rarely about brute strength alone. It depends on knowledge of plants, tracking skills, memory of seasonal cycles, and an ability to negotiate within the group. Calories may be the fuel, but information is the currency. A brain that could integrate both, balancing ecological know-how with social tact, would have an advantage that went beyond sheer energy intake. Another underappreciated piece of the puzzle is variability. Paleo-environmental studies show that Africa between 2 million and 500,000 years ago was a land of shifting rainfall, expanding and contracting lakes, and alternating mosaics of forest and grassland. Populations had to cope not with one stable food source, but with constant change. This context weakens the appeal of any single magic bullet explanation. Instead, adaptability itself becomes the trait under selection. A flexible diet that included meat, roots, cooked foods, and perhaps occasional chemical novelties could have buffered groups against sudden shortages. In that sense, mushrooms may not have been the primary engine of brain growth, but they were part of the broader ecology of experimentation. Hominins that explored new niches, whether through taste, tools or fire, had a better shot at weathering instability. Looking outward to other lineages underscores the uniqueness of this cocktail. Large carnivores like lions had calories in abundance, but they lacked the social depth of humans. Other primates experimented with diverse diets, but they did not pair it with regular fire use. Humans alone seem to have blended caloric innovations with social and cultural ones, creating a feedback loop that magnified both. The rise of our brains was probably not the result of a single cause, but of several processes colliding in the right order over deep time. So when we weigh calories against chemicals, it may not be a choice at all. The story is not about which single factor flipped the switch, but how multiple streams of adaptation converged to sustain a runaway brain. Cooking, hunting, sharing, and yes, the occasional strange meal on the savannah, all of these layered together to feed an organ that never stopped asking for more. What were elephants doing high on iboga, and did humans copy them? In the dense rainforests of Central Africa grows a small shrub called Tabernanthe iboga. Its roots contain a potent alkaloid called ibogaine, a compound capable of inducing intense visions, altered bodily sensations, and in high doses, severe toxicity. Today it is most widely known through ritual use in Gabonese initiation practices, but Norman Ohler and a handful of ethnographers have pointed out that long before humans were experimenting with iboga, elephants may have been digging up and consuming the roots themselves. Accounts from forest communities describe elephants seeking out iboga during certain seasons, tearing up the earth with their trunks and consuming quantities of the bitter plant. The behaviour is not random. Elephants appear to chew and then enter a state of unusual stillness, swaying gently as though under the influence. Observers have debated whether this is intentional intoxication or accidental foraging, but the pattern recurs often enough that it has become part of local ecological knowledge. And when animals as large and intelligent as elephants experiment with psychoactive plants, it forces us to rethink human uniqueness. Curiosity about chemical states is not confined to one species. For hominins living near or within these forests around 1 million years ago, such behaviour would not have gone unnoticed. Elephants were central to the environment, not just as prey, but as ecosystem engineers. Their trails carved through vegetation, their dung spread seeds, and their sheer size shaped the landscape. If early humans watched elephants dig for roots and then enter altered states, they might have been tempted to try the same substance. Foraging was never about eating only the safe and familiar. As we saw with mushrooms, experimentation was part of survival. A root chewed by elephants might have seemed a signal of edibility, even if the outcome was unpredictable. The possibility that iboga entered the human story this way remains speculative, but it rests on an ecological truth. Humans often learn what is edible or medicinal by observing other animals. Chimpanzees eat bitter piths that function as natural antiparasitics. Birds consume clay to neutralize toxins in seeds. The line between food and drug in such behaviors is thin, and hominins were part of this continuum. If iboga exposure began with imitation of elephants, it would not be the first or last time our species copied animal foraging strategies. What makes iboga particularly interesting in the human evolutionary timeline is its intensity. Unlike psilocybin, which tends to produce shorter-lived alterations, ibogaine can sustain visions and disorientation for many hours. Even small doses produce strong bodily effects: nausea, slowed coordination, and dreamlike imagery with eyes open. This raises a question not just about why early humans might have tried it, but whether such experiences shaped their relationship to the forest around them. Did iboga make the jungle feel alive with agency? Did it turn ordinary landscapes into realms of significance? We cannot know, but it is worth asking why such powerful plants persisted in human interest for so long. The archaeological record cannot show us a fossil of iboga chewing, so here we must rely on analogy and modern ethnobotany. What we do know is that humans in Central Africa have used iboga for centuries at minimum, perhaps millennia, and they often tell myths linking the plant to animals who first discovered it. Elephants remain prominent in these tales, not as symbols but as active participants in transmitting knowledge. Even if the details are mythologized, The underlying suggestion that humans watched animals and learned chemical lessons fits with everything we know about how foragers engaged with ecosystems. The elephant's route, then, may be less about a single chemical event in prehistory and more about the larger pattern, that our species' path through evolution was shaped by curiosity not just toward calories, but toward substances that changed how the world was perceived. Elephants eating iboga remind us that altered states are not alien intrusions into nature. They are woven into the behaviours of many species, and humans, ever the watchers and imitators, could hardly have resisted. Whether iboga shaped our evolution is an open question, but its presence in the forests and its allure to giants of the animal kingdom suggests it was always there, waiting to be noticed. When we linger a little longer on iboga, we begin to see how unusual it is compared to most other plants in the hominin environment. Many edible roots provided starch or mild medicinal qualities, but iboga stood apart for the intensity of its alkaloids. This meant that any early encounter would likely have been memorable, whether pleasant, confusing, or frightening. Unlike tubers or nuts, iboga could not become a daily staple. Instead, it was something extraordinary, a plant that demanded respect. That very difference may have carved out a niche for it in the lives of those who dared to experiment. Consider how foraging groups often built a catalogue of the land's resources, passing down knowledge orally through generations. A plant that caused hours of dizziness or vivid dreams would not be easily forgotten. Even if some members of a group reacted badly, others might have seen visions or felt a surge of energy that was interpreted as meaningful. In that sense, iboga may have entered the forager's mental map not as food, but as a marker of power. Observing elephants return to the plant at intervals could have reinforced this perception, suggesting that the root was not merely edible but special, reserved for moments of need or curiosity. This raises another subtle possibility, that iboga did not have to be consumed often to matter. If it was tried only rarely, it could still have left a cultural imprint. In evolutionary terms, occasional encounters with powerful plants may not alter genes directly, but they can alter traditions, practices, and the shared stories that knit small groups together. In the deep past, where myths and ecological memory were not separate categories but part of daily life, a route that made one feel both ill and visionary could have influenced how people talked about the land, the animals, and themselves. Modern accounts from Gabon and Cameroon describe iboga as a teacher plant, one that helps initiates face their fears, recall memories, and enter dreamlike states while awake. These practices cannot be directly mapped back to 1 million years ago, but they remind us of the continuity of human curiosity. The endurance of iboga traditions into the present shows that the plant has long held a place in the repertoire of substances that mediate between body, mind, and environment. If elephants once introduced humans to iboga, the legacy of that encounter may have outlasted countless other forgotten experiments with leaves, berries, and roots. In the end, iboga invites us to imagine hominins not only as hunters and toolmakers, but as experimenters with chemistry. Just as fire changed diets and stone reshaped landscapes, plants like iboga added another dimension to the story, one where the forest itself offered substances that could twist perception, stir the body, and leave behind an indelible impression. Whether or not it steered evolution, it certainly reminded our ancestors that survival was not just about finding enough to eat, but about learning when to approach, when to avoid, and when to dare the unknown. What if the real story of becoming human was not about sudden sparks of genius, but about weather that refused to stay steady? Around 3,700,000 years ago, the African continent began to enter a period of greater environmental variability. Lakes swelled and then dried, rivers shifted, grasslands spread, and then retreated into woodlands. The backdrop of human evolution was not a stable stage, but a shifting one, with the scenery changing every few tens of thousands of years. This is the central idea behind what has been called the Variability Selection Hypothesis, that it was not one type of environment that shaped us, but rather the constant need to adapt to new ones. Recent work, like the synthesis published in the Proceedings of the National Academy of Sciences in the year 2022 by Andrew Cohen and colleagues, has given us one of the clearest pictures yet of this long rhythm of change. By compiling dozens of environmental records across the African continent, they showed that variability increased steadily from about 3.7 million years ago onward. This rise was not smooth, but patterned, showing clear cycles tied to the pull of Earth's orbit. Every 400,000 years, insolation changes altered rainfall patterns and seasonality, leaving marks in sediments, pollen, and isotopes. These orbital rhythms sat atop an even longer trend toward instability, as global ice sheets expanded and ocean currents shifted. Yet, when the researchers compared these environmental fluctuations to the record of mammalian speciation and extinction, the results were humbling. The expected correlation was weak or absent. Variability alone did not line up neatly with bursts of new species or waves of disappearance. In other words, while the African landscape certainly changed again and again, the animals living there, including our own ancestors, did not respond with equally dramatic pulses of turnover. This suggests that the relationship between climate and evolution is more tangled than we might wish. For early hominins, these swings would have been deeply felt even if they did not always leave genetic signatures of new species. A basin that held a permanent lake for centuries might have supported fish, reeds, and hippos, only to shrink to a seasonal swamp that forced primates to forage on roots and dry tubers. Populations might not have gone extinct in these intervals, but they would have been pressed to move, to innovate, or to mix with neighbours in new ways. Variability may not have directly driven speciation, but it made survival a matter of flexibility. This has implications for how we think about human origins. It is tempting to tell the story as though one event or one substance changed everything. The climate record cautions us that evolution happened against a restless background, one where no single food or behaviour guaranteed long-term success. Instead, adaptability itself became the enduring trait. We see this lesson most clearly in the fossils of Eastern Africa, where the record of lakes and soils matches the story of hominin persistence through both wet and arid phases. In that light, variability was less a sculptor and more a stagehand, constantly rearranging the scenery. Hominins had to be ready to play their part on open savannahs, in patchy woodlands, or near unstable lake shores. The absence of a simple link between variability and speciation does not make the story less interesting. It makes it more realistic. The world did not hand us progress. It handed us a changing script and left us to improvise. And so, we are left with the question, if climate change alone did not dictate our evolutionary leaps, then what else was at work in those long African millennia? What pressures, choices, or accidents filled the spaces between drought and flood, forest and grassland? It is in this uncertainty that the search for our origins remains alive. One of the striking things about the environmental record is how localized its stories can be. A dry spell in the Turkana Basin might not coincide with drought in the Rift Valley further south, and yet both show evidence of change layered into their sediments. This means that hominin groups moving across the landscape would not have encountered a single African climate, but a patchwork of shifting mosaics. A corridor that was grassy savanna in one century might turn into thorn scrub or patchy woodland in the next. In this sense, variability was not just about time but about space. Different valleys, lakes and highlands each had their own rhythm of wet and dry, their own particular combinations of plants and animals. The fossil record of herbivores mirrors this patchwork. Antelope species in particular are sensitive indicators of grassland versus woodland proportions. Over the last 3 million years, their composition shifts back and forth in ways that reflect local ecological oscillations. But these changes rarely align with sudden extinctions. Instead, species often retreated to refuges or expanded into new niches rather than disappearing outright. This resilience hints that variability acted less as a hammer and more as a sieve, rewarding versatility rather than favouring complete replacement. For hominins who lacked hooves, horns or wings, versatility may have meant dietary breadth, cooperative foraging and mobility. Another detail from the climate reconstructions is the role of orbital cycles. The 400,000-year rhythm linked to Earth's eccentricity shows up clearly in lake and soil records. To imagine its impact, think of generations of hominins who lived during wetter phases with reliable water and dense vegetation. Thousands of years later, their descendants faced more erratic rainfall, rivers that vanished seasonally, and harsher dry seasons. Over evolutionary time, this repeated training in unpredictability could have left a cultural legacy as well as an ecological one. Stories, practices, and survival strategies may have been passed down not because conditions were stable, but precisely because they were not. It is also worth noting what the fossil and environmental datasets cannot yet tell us. Gaps in sampling mean that many subtle shifts are invisible. Small-scale adaptations like changes in behaviour or local population movements do not always leave signatures in bones or pollen. Hominins may have responded to variability through social changes, migrations, or tool innovations that are still hidden from us. In this way, the climate record becomes a canvas of broad strokes rather than a finely detailed painting. The big swings are visible, but the lived experience remains partly out of reach. This does not lessen the importance of variability as a concept. Instead, it sharpens the mystery. Climate was clearly a restless companion in our story, but the connection between shifting skies and shifting species is more nuanced than a direct cause and effect chain. It suggests that to understand why hominins survived and evolved, we need to look not only at the climate itself, but at the strategies of flexibility, mobility, and improvisation that allowed them to navigate it. That balance between ecological backdrop and human ingenuity may be where the true story of our survival lies. How close did our species come to disappearing before the story had even begun? Genetic evidence suggests that sometime between 200,000 and 70,000 years ago, Homo sapiens passed through a bottleneck so narrow that the global population may have shrunk to just a few thousand individuals, perhaps as few as 1,500 breeding adults. To imagine the scale of this fragility, picture the entire future of humanity balanced on a community smaller than a modern village. Every language, every technology, every idea yet to come depended on the survival of this threadbare lineage. The reasons for such a bottleneck are still debated. Some argue that climate stress played a role. Africa during this period was no stranger to shifting conditions, with oscillations between wet phases that swelled lakes and rivers and arid intervals that turned landscapes into deserts. Droughts could have fractured populations, isolating groups in ecological refuges such as the Ethiopian highlands, the Rift Valley lakeshores, or the coasts of southern Africa. In such refuges, survival would have been precarious, relying on patchy resources and the ability to innovate quickly. Other hypotheses look to volcanic catastrophes or disease outbreaks, but the evidence is mixed. The famous eruption of Mount Toba about 74,000 years ago once seemed like a neat explanation for a population crash. But more recent studies suggest that the demographic squeeze of our species began earlier and cannot be pinned on a single eruption. Instead, it appears that multiple pressures over tens of thousands of years gradually funneled our numbers down. The bottleneck was not an abrupt cliff, but a narrowing canyon, through which only the most adaptable groups passed. Living in such small populations carried its own risks. Inbreeding could have weakened resilience, making individuals more vulnerable to disease or genetic defects. Small founder groups often face what biologists call drift, the random loss of genetic diversity simply because there are too few people to carry all the possible variations. The fact that we emerged on the other side of this period with enough diversity to thrive is remarkable. It suggests that either survival refugees were more numerous than we think, or that gene flow between them occasionally reconnected the strands. In such precarious circumstances, any factor that gave a survival edge might have been decisive. Reliable food sources, cooperative social networks, and technological ingenuity would all have mattered. Some speculative voices, like those inspired by the Stoned Ape Hypothesis, even wonder if encounters with psychoactive plants and fungi offered occasional advantages, whether through encouraging group cohesion, easing conflict, or stimulating creative problem-solving. We cannot prove such claims, but within the fragile ecology of bottleneck populations, even minor edges could ripple outward across generations. The genetic bottleneck reminds us of how contingent our survival was. The humanity we know today is the descendant of a population so small that chance alone could have erased it. When we think about our species' later expansion across the globe, we should not forget this earlier moment when existence balanced on the edge of disappearance. The bottleneck is a sobering reminder that evolution is not a story of inevitability. It is a story of narrow escapes, fragile refuges, and the persistence of groups who found ways, through environment, through ingenuity, perhaps even through strange meals from the landscape, to carry the lineage forward. When we follow the thread of this bottleneck more closely, it becomes clear that it was not just a genetic event but also an ecological one. To persist in landscapes that could swing from lush to barren within the span of a few generations, Homo sapiens had to learn how to squeeze sustenance out of marginal habitats. Archaeological traces from coastal South Africa hint that some groups turned to the sea, gathering shellfish, seaweed, and even birds' eggs when inland resources failed. Inland, small game, hardy tubers, and drought-resistant seeds may have filled in gaps. These were not glamorous meals, but in the arithmetic of survival, every calorie counted. Another overlooked feature of small populations is the fragility of knowledge itself. When only a few hundred individuals carry a tradition, a single lost elder or an interrupted migration can erase skills that took centuries to develop. Fire-making techniques, plant lore, or seasonal tracking could vanish in a single unlucky generation. Yet, the fact that our ancestors endured suggests that some knowledge systems were maintained and passed on with extraordinary care. This highlights the role of memory, storytelling, and teaching long before writing existed. The bottleneck was not only about genes, but about cultural bottlenecks, what information was preserved and what was forgotten forever. There is also a geographic dimension to consider. Genetic signals imply that refugees were scattered, perhaps separated by hundreds of kilometres of uninhabitable terrain. For groups to reconnect across such barriers required mobility and persistence. Occasional contact may have allowed genes, tools, and ideas to flow between populations, keeping diversity alive. The archaeological record sometimes shows sudden shifts in tool styles or resource use, which may reflect these rare exchanges. A piece of stone technology turning up far from its usual region is not just an artifact, it is a clue that even in hard times, humans reached beyond their immediate circles. Modern comparisons can help us imagine the scale of this fragility. Conservation biologists warn that animal species often decline rapidly once populations dip below a few thousand individuals, as the loss of genetic variability makes them more vulnerable to disease or climate change. By those standards, Homo sapiens should have been on the brink of collapse. That we were not may speak to the unusual flexibility of our species. Social bonds, shared child-rearing, and cooperative foraging may have provided buffers that numbers alone could not guarantee. Reflecting on this period, we are reminded that survival was not assured. For tens of thousands of years, the existence of Homo sapiens was an open question. That we emerge from such scarcity to later transform the planet is one of evolution's great paradoxes. The might of billions today rests on the narrow survival of a population that could have vanished without leaving a trace. What if the first time an early human felt the ground shift beneath their feet in a state of strangeness? They were not alone. Around 100,000 years ago, our species was already scattered across Africa and beginning to move outward, living in small but resilient groups bound together by shared labour, shared danger, and shared food. It was within such groups that the occasional taste of something unusual could begin to mean more than a private accident. When an individual consumed a mushroom, a root, or a fermented fruit and felt their perception wobble, others would have noticed. The strange behaviour, the laughter, the trance-like silence, the dancing, these became visible, communal events, and because we humans are deeply social creatures, curiosity would have led others to follow. In that moment, a solitary foraging experiment became a shared ritual. We must imagine the context. Long nights around fires, storms keeping groups in caves or shelters, migrations halting by water sources. Within those pauses of daily survival, the ingestion of unusual plants or fungi could take on a patterned role. Archaeological traces of symbolic behaviour from this period, such as ochre use and beadwork, remind us that humans were already beginning to create meaning beyond the practical. If shells and pigments could become markers of identity, then unusual foods that change perception could easily become tools for binding communities together in new, less tangible ways. The altered state may not have been sought simply for novelty, but for the cohesion it created. Anthropologists studying hunter-gatherer groups today often remark on how rituals involving song, rhythm and dance bring people into sync, calming tensions and reinforcing unity. If certain foods or mushrooms were discovered to deepen that synchrony, they could have been woven naturally into the fabric of these proto-rituals. It is plausible that a successful hunt, or a seasonal gathering, was punctuated not only by feasting, but also by experimenting with such substances. Over time, repetition could transform these experiments into traditions, and traditions into rituals. The earliest shamans may not have been spiritual leaders as we think of them now, but simply individuals who had unusual experiences survived them and were then seen as guides into those altered states for others. What makes this period significant is not just that humans consumed these substances, but that they may have started to structure their use. Instead of accidental or solitary, the ingestion of mushrooms or other psychoactive plants could have been framed within rules. Who takes them, when, and for what purpose? Some groups might have associated them with fertility, others with hunting luck, and still others with communication with unseen forces. The details are beyond our evidence, but the scaffolding of ritual, the repetition, the communal participation, the layered meanings, was already emerging in human life by 100,000 years ago. This raises a fascinating possibility. Perhaps the very first sense of religion, not as belief in gods, but as shared awe, was linked less to abstract doctrine and more to shared experience under altered states. Awe binds groups. When people collectively step outside the ordinary, even briefly, they return with bonds that feel stronger. We see hints of this in every society that followed, where substances and ceremony are intertwined. Yet here, at this early stage, it may have been as simple as a group gathered around a fire, eyes dilated, senses heightened, feeling both fear and wonder together. It is difficult to prove such moments from stone tools and bones alone, and as always we should be cautious. But the plausibility rests in human nature itself. Curiosity, pattern-making, and the desire to share experience are all traits that long predate agriculture or cities. Once the spark of ritual was lit, it never left us. Whether or not mushrooms were the spark, they were certainly among the strange foods available in these landscapes, ready to be tried, remembered, and perhaps woven into the early fabric of symbolic life. And so we are left with an open thought. When humans first began to gather not only to eat, but to transcend, was that the true beginning of ritual? If so, it means the earliest ceremonies may not have been about worship or sacrifice, but about stepping into mystery together, guided not by a priest or text, but by the earth's hidden chemistry. If we step carefully into the imagined circle of those early gatherings, another layer comes into view. Altered states were not only about binding the group through awe and spectacle, they may also have created a rare social flexibility. In small bands of hunter-foragers, tensions were inevitable, rivalries, jealousy, disputes over food or mates. A shared state of strangeness could temporarily dissolve these rigid roles. The stern elder might laugh uncontrollably, the confident hunter might stumble into silence, the timid youth might suddenly speak with authority. These reversals, even if fleeting, may have loosened the knots of social life, allowing groups to reset their balance. Ritual highs, then, may have functioned as social technology long before the concept of technology extended beyond stone. It is worth considering the sensory environment of such rituals. Firelight flickering across ochre-stained skin, the drumbeat of feet or sticks, voices echoing in natural caves, all amplified by a body under the influence of chemistry. These are the kinds of multisensory experiences that neuroscience today recognizes as profoundly altering memory. For early humans, such rituals would not fade quickly. They would linger, becoming stories retold the next morning, shaping expectations for the next gathering, seeding myth long before myth had language. When groups returned to certain spots, riverbanks, caves or glades, they may have remembered not only the food and shelter those places provided, but also the uncanny experience of having felt other. Landscape itself could become sacred through the layering of these repeated extraordinary encounters. Some anthropologists have suggested that the origins of leadership may be tied to these moments. Not leadership in the hierarchical sense we know later, but in the subtler sense of who guided others into and out of unusual states. Those who showed calm during disorienting experiences or who claimed to have seen something meaningful, might have gained influence. This would have been a fragile form of authority, but it points to how social structures can emerge from shared inner experiences. In this view, the first ritual highs were not only proto-religious, but also proto-political, shaping dynamics of trust, charisma, and cohesion. The archaeological record will likely never show us direct traces of such moments, yet indirect hints remain. The choice to collect pigments, to string shells, to mark bodies with adornments suggests humans were already comfortable with the idea that the ordinary world could be modified, enhanced, or symbolically reimagined. In that light, the use of psychoactive plants or mushrooms seems less like an anomaly, and more like a natural extension of the same tendency, the refusal to settle for the purely practical. A root could be food, but also medicine, but also a pathway into vision. A mushroom could be sustenance, or poison, or portal. Perhaps the most striking thought is that these early rituals may not have been about answers at all, but about questions. They were ways of stepping together into uncertainty and coming back with stories. In that sense, ritual highs were less about escaping reality, and more about enlarging it, reminding early humans that the world was not just what they could see in daylight, but something stranger, layered, and shared. That reminder has followed us ever since. What if the great difference between us and our closest cousins was not in the cut of a tool or the shape of a skull, but in how we chose to alter the ordinary? Around 50,000 to 40,000 years ago, the world held more than one kind of human. Neanderthals endured across Europe and Western Asia, skilled hunters with sturdy builds, capable of surviving harsh winters and shifting climates. They crafted tools, wore hides, and made use of fire. Yet something subtle may have separated their path from ours, the willingness to experiment with substances that changed perception. Writer Norman Ohler has suggested that Neanderthals may have been too sober for their own survival, while Homo sapiens leaned into experimentation with plants, fungi, and fermented foods. It is a provocative thought, not one that rests on hard evidence, but on patterns that anthropology has shown us again and again. Groups that find ways to expand the imagination, through song, art, rhythm, or chemistry, often leave behind deeper symbolic traces. By the time sapiens were expanding through Africa and into Eurasia, their willingness to test the limits of body and mind may have given them a cultural fluidity that Neanderthals never quite matched. To picture this difference, imagine two evening fires. Around one, a Neanderthal group huddles close, conserving energy, following routines that had worked for generations. Their lives were built around pragmatic survival, meat from the hunt, skins for warmth, tools to cut and scrape. Around the other, a sapiens band sits not only with food, but perhaps with odd roots or mushrooms gathered earlier in the day. They may sing, laugh, or sink into reverie together, turning the fire into a stage for shared strangeness. The comparison is simplified, of course, but it reflects a possibility. One group repeated the known, while the other nudged at the unknown. The archaeological record hints at these contrasts without giving us certainty. Neanderthal sites show remarkable survival skills, but relatively limited evidence of symbolic play during this late period. By contrast, sapiens were producing ornaments, pigments, and early musical instruments. Could altered states have reinforced these practices, making experimentation itself a survival trait? If shared visions deepened bonds, if curiosity rewarded exploration, then the drug culture of sapiens may have contributed to their adaptability as environments shifted and new challenges arose. We should be cautious not to reduce this to a tale of superiority. Neanderthals thrived for hundreds of thousands of years without needing such practices. But when climates swung wildly and competition with other humans grew fierce, perhaps their steadiness became a limitation. Sapiens' occasional willingness to step outside sober routine may have opened cognitive and cultural doors that Neanderthals left closed. This does not make one species better than the other. It only shows how survival sometimes favours risk, even risky curiosity. In this view, the disappearance of Neanderthals may not only be a story of climate stress or dwindling resources, it may also reflect a divergence in cultural willingness. One species cautious, the other willing to taste, try and dream. That willingness, fragile and strange, may have tipped the balance toward the future we inherited. When we weigh this idea more carefully, it is not about claiming that Neanderthals lacked imagination altogether. They buried their dead, they shaped tools with care, and they endured in some of the harshest conditions our planet could throw at them. But ritual intoxication, if sapiens had begun to weave it into group life by this time, may have represented a different kind of cultural glue, one that created narratives not tied only to survival, but to transformation. The gathering around intoxicants can foster shared memory, inside jokes, visions told and retold, until they form a common mythology. If Neanderthal life remained largely pragmatic, then their sense of identity may have stayed narrower, tied to hunting territories and kinship alone, while sapiens began to sketch worlds beyond the visible. Archaeologists have long noticed that symbolic artifacts from Neanderthal sites are comparatively rare and tend to appear later, perhaps even through contact with our own ancestors. By contrast, the flourishing of ornaments, pigments, and instruments among sapiens suggests a cultural energy pushing outward. If psychoactive plants and fungi helped intensify such expression, then this difference could have mattered deeply. Altered states can make landscapes feel enchanted, turning an ordinary tree into a landmark or a cave into a portal. Groups who shared those altered perceptions might return to the same places, reinforcing bonds with the land itself. Such patterns could have made sapiens more mobile, more experimental, and more adept at weaving diverse habitats into their way of life. There is also the question of adaptability. A community willing to consume strange plants is, by definition, a community willing to take risks. Most experiments would have ended in disappointment or illness, but occasionally the outcome would be beneficial, discovering new medicines, tolerable foods, or ritual experiences that bonded the group. Over millennia, this culture of curiosity may have created a feedback loop, where the expectation of novelty itself became a survival tool. If Neanderthals, by contrast, relied on strategies that had already worked for thousands of years, they may have been less inclined to gamble on the unknown. In a stable world, this conservatism would be wise. In a rapidly shifting Ice Age environment, it might have been dangerous. Of course, we must recognise the limits of our evidence. No direct traces of mushroom use or plant intoxication have been uncovered for either group at this timescale. What we have are hints and analogies, combined with patterns observed in recent human cultures. The hypothesis that Neanderthals were too sober for the future remains speculative, but it is a speculation rooted in a real question. Did willingness to court altered states influence not just how we lived, but who ultimately remained to tell the story? Why would ancient artists paint mushrooms sprouting from the bodies of shamans? Around 7,000 years ago, in what is today the arid Tassili Nadja plateau of Algeria, hunter-gatherers left behind some of the most intriguing rock art on Earth. These images, etched and painted on sandstone walls, show figures with insect-like features, animal masks, and in certain cases clusters of mushrooms connected to their limbs or held in their hands. One famous painting depicts a tall, humanoid figure with what seem to be mushrooms radiating from the body, as if growing out of the flesh itself. Another shows smaller human forms holding mushroom-like objects, arranged almost ceremonially. To modern eyes, these depictions appear uncanny, but to archaeologists and ethnographers they suggest something remarkable. That ritual use of psychoactive fungi had not only entered human life, but had become important enough to be immortalized in stone. To appreciate this art, it is useful to remember the environment. 7,000 years ago, the Sahara was not yet the vast desert we know. It was greener, dotted with lakes, grasslands, and herds of animals. Early pastoralists lived there, herding cattle, gathering wild plants, and painting the walls of their shelters with vivid scenes of daily and spiritual life. Among the cattle and hunters, the mushroom figures stand out. They are not incidental decorations, but deliberate, repeated motifs. The implication is that mushrooms held symbolic weight, perhaps as tools of trance, transformation, or communion with non-human forces. What makes these images even more compelling is how they echo patterns seen across many cultures separated by vast distances. In Siberia, shamans are often associated with fungi like the red Amanita muscaria. In Central America, carved stones and codices show mushroom-headed figures linked to ritual practice. The recurrence suggests a continuity in how humans experienced and represented the altered states induced by fungi, not as random intoxication, but as a path to other realms. The Algerian paintings extend this timeline deep into prehistory, showing that such associations were present thousands of years before written records. We must be careful, however. Not every mushroom-like drawing can be definitively linked to psychedelic use. Some scholars argue that the shapes may be stylized plants, symbols of fertility, or purely decorative. Yet the clustering, the placement on human figures, and the ethnographic parallels make the psychedelic interpretation persuasive. And if true, it means that long before the rise of organized religion or urban civilization, groups in North Africa were already formalizing rituals around substances that change consciousness, and leaving behind a visual record of their significance. The paintings invite us to consider how ancient peoples framed these experiences. Were mushrooms thought of as gifts from the gods, as medicine for the spirit, or as guides through the thresholds of life and death? We cannot know for sure, but the fact that they were painted at all suggests reverence. Art preserves what matters, and in this case, mushrooms mattered enough to be etched into the collective memory of a community. They remind us that the line between sustenance, symbol, and sacrament has always been thin, and that the human impulse to seek transcendence through the natural world is as old as our ability to paint a wall. See 2. Looking more closely at the Tassili art, another detail emerges. The mushroom-bearing figures are often shown in motion. Their limbs are stretched in postures that resemble dance, and their bodies are surrounded by patterns of dots and lines, as if sound or energy were emanating from them. This kind of visual language, abstract yet expressive, suggests more than just a record of what was eaten. It may have been an attempt to capture the feeling of the experience itself, the rhythms, the visual distortions, the sense of being caught in something larger than the self. In this way, the rock art functions almost like an early diary, a way of saying, this is what it felt like when we crossed into that state. The timing is significant too. By 7,000 years ago, pastoralist groups were adapting to the drying Sahara. Rituals likely played an important role in stabilizing identity as resources became less predictable. In that context, mushrooms may have been more than entertainment or curiosity. They may have been seen as anchors, ways of binding a group together during uncertain transitions. If communities painted shamans sprouting mushrooms, it could have been a declaration. Our survival is tied not only to herding and hunting, but also to the worlds we touch when we alter our minds together. Another striking feature is the hybrid quality of the figures. Some seem part human, part insect, with antennae or compound eyes suggested by the patterns. Others blur into animal shapes, recalling the way many later shamanic traditions describe transformations into non-human forms during trance. This imagery supports the idea that mushrooms were not simply consumed, but woven into a broader cosmology where boundaries between species and realms could be crossed. For a community living in close relationship with animals and the land, such visions may have reinforced respect for the more than human world. Importantly, the persistence of these images shows that the mushroom motif was not fleeting. It was repeated across generations of artists, long enough to establish a symbolic tradition. This continuity underlines the role of altered states in shaping cultural memory. Just as ochre beads or animal carvings reveal symbolic thinking, mushroom depictions reveal how humans chose to represent inner experiences, not just outer events. The walls of Tassili don't only tell us who hunted what, they tell us who dreamed and how they made those dreams visible. When we stand before these paintings today, we're not only looking at ancient art, but at a record of human imagination trying to fix the ineffable in stone. And while we cannot fully recover the voices of those shamans, the painted mushrooms remind us that for them, transcendence was not abstract. It sprouted from the earth, was eaten by the mouth, and was carried into the body until it blossomed again, etched forever onto rock. 40,000 years ago, across Ice Age Europe, some of the earliest cave paintings began to bloom into existence. They were not sketches made casually at the mouth of a shelter, but works hidden deep inside limestone caverns, painted by torchlight where no daylight could reach. To enter those places was already to step into another world, a world of flickering shadows, echoing sounds, and silence broken only by breath. It is here that humans painted bison, horses, lions and shapes that seem less like animals and more like visions. Picasso, after visiting the caves of Lascaux in the 20th century, is said to have remarked, "We have learned nothing." He meant that the power of those paintings was so raw, so immediate, that they eclipsed millennia of art that followed. But what was happening in the minds of the first artists when they left such images? Some researchers have proposed that these paintings may reflect experiences in altered states. The twisting, glowing lines, the surreal motion of animals leaping across walls, the geometric patterns that look like tunnels or bursts of light, all resemble the kind of imagery reported in trance, dreams, and psychedelic visions. To paint such forms in total darkness, lit only by the unstable flare of torches, was to amplify the sense of unreality. The flicker of fire would have made the painted animals appear to move, to breathe, to shift. The cave itself became alive. The setting matters. Many of the most famous paintings are not easily accessible. They require crawling through narrow passages, descending into the bowels of the earth, squeezing past obstacles before reaching the main chambers. Such journeys alone would have heightened tension and anticipation. For a group entering with chance, fire, and perhaps substances gathered from the world above, fungi, herbs, fermented fruit, the transition into another state would have felt inevitable. By the time they reached the walls where paintings were made, their bodies and minds may have already been primed for transformation. The animals themselves are not rendered as they would be seen in ordinary hunting scenes. They're often oversized, elongated, repeated in layered outlines, or fused together. Some have multiple heads or extra legs, as if the painter wanted to capture motion or multiplicity rather than simple form. Others appear ghost-like, transparent, almost dissolving into the rock. These features parallel what neuropsychologists call entoptic phenomena, visions of shapes and distortions produced in the visual cortex during altered states. Spirals, grids, dots, and morphing animals are common reports in shamanic contexts worldwide. It is striking, then, that the same motifs appear in caves tens of thousands of years ago. The possibility that early artists were also early trippers does not mean that every painting must be reduced to hallucination. Hunting magic, storytelling, teaching, and identity marking may all have played roles, but it does mean that we cannot ignore the atmosphere of those painted chambers, underground temples where vision was deliberately shifted, whether by deprivation, ritual, or ingestion of the strange. To stand before a wall where a mammoth charges forward, lit by fire, surrounded by rhythmic sound, was not a neutral experience. It was immersive, sensory, and likely transformative. What we can say with confidence is that these were not mere decorations. They were events captured in pigment. They were places where humans pushed perception beyond the ordinary, where art and altered awareness merged into something neither one nor the other. If so, then the caves that still glow with ochre and charcoal are not only our oldest art galleries, they are our oldest theatres of the mind, where humanity first painted what it saw when the doors of perception cracked open. Another clue that cave painting was bound up with altered perception comes from the very choice of pigments and techniques. Ancient artists were not simply using what was convenient. They ground minerals into fine powders, mixed them with animal fat or plant resins, and sometimes blew them through hollow bones to spray pigment across the stone. This act of spraying created a mist that clung to the wall, but also entered the lungs of the painter. Whether intended or not, inhaling such powders in a dark chamber filled with smoke could have induced dizziness, euphoria, or even mild hallucinations. Combined with the low oxygen and the hypnotic repetition of hammering, scraping, or chanting, the whole environment blurred the line between art-making and trance. There is also the question of sound. Caves amplify and distort noise in ways that are difficult to predict. A single clap can echo like thunder, and a human voice can bounce back warped into something almost unearthly. Archaeologists who have studied the acoustics of painted caves in France and Spain found that the densest clusters of art often appear in areas with the strongest echoes. It is as if the walls themselves were chosen because they seemed alive, responding to sound, guiding the painter toward resonance. Imagine chanting, drumming, and seeing. The walls respond with images that seem to glow and pulse. For people living 40,000 years ago, this was no metaphor, it was experience. What these early experiments tell us is that art was not isolated from ritual. It was embodied, collective, and sensory. The cave was a stage where every sense could be bent: sight through firelight and pigment, hearing through echoes, breath through smoke, touch through rough stone, and mind through exhaustion or intoxicants. To step into that stage was to step out of ordinary time. When we look back at those paintings today, we often view them in sterile museum reproductions or glossy books. We forget the claustrophobia of crawling into darkness, the heat of torch smoke, the trembling of voices inside stone corridors. To the people who made them, these were not images but encounters. And perhaps this is the deeper point. Whether or not psilocybin or other substances were directly involved, the cave environment itself functioned like a psychedelic. It altered the chemistry of the brain through stress, awe, and sensory overload. It carried people to a threshold where images came alive and animals spoke. We cannot prove if mushrooms were part of that journey, but we can say with certainty that humans were already seeking ways to leave the ordinary behind. That hunger to cross thresholds, to mix vision with meaning, seems almost inseparable from what we call being human. The paintings, glowing even now, remain our first surviving evidence that art and altered states walked hand in hand from the very beginning. What if the blazing shrub that Moses described on the slopes of Sinai was not simply a miraculous flame, but a vision brought on by a plant that carried its own fire inside? The biblical story is one of the most famous in human memory. A shepherd approaches a bush that burns without being consumed, and from it comes the voice of a god. To us today it sounds like a moment outside of time, impossible to anchor to geology or biology. Yet some Israeli researchers have suggested that the story may be more earthly than it seems. They point to the acacia trees and shrubs that dot the deserts of the Sinai and Negev. Acacia, especially when burned or prepared in certain ways, contains compounds closely related to dimethyltryptamine, or DMT, one of the most potent psychedelic substances known. The idea is startling, that the burning bush was not simply fire but chemistry, and that Moses may have stood in a cloud that bent his vision toward the divine. To understand the context, we have to imagine the Sinai desert more than 3,000 years ago. Sparse rainfall, wide valleys, and scattered thorn trees provided little comfort to herders and wanderers. The acacia was one of the few plants resilient enough to survive such dryness. Its wood was dense and burned with an unusual intensity, while its resin carried a distinctive fragrance. For pastoralists, burning such wood for warmth or ritual would not have been rare. What they may not have understood in a chemical sense was that inhaling the smoke could alter perception. Modern laboratory work confirms that acacia species in the region contain alkaloids with psychoactive potential. Alone, they may not induce strong effects, but combined with other plants or under conditions of fatigue, fasting, and stress, the smoke could have produced visions vivid enough to be remembered as encounters with a god. Some anthropologists propose that the power of the burning bush story lies not in its uniqueness, but in its familiarity to those who lived it. In desert societies, where survival often depended on endurance and trust in unseen forces, altered states may have served as proof that the divine was real and present. The vision of a fire that does not consume could have been less about physical observation, and more about the overwhelming impression of seeing light where no ordinary flame should be. For Moses, already in exile, already primed for revelation, the experience could have felt absolute, undeniable, and binding enough to change the course of a people's history. Skeptics point out that we cannot know whether Moses ever existed as described, let alone whether he inhaled DMT-laden smoke. Yet this hypothesis highlights a wider truth. Across cultures, from Siberia to the Amazon, sacred plants and altered states are woven into the fabric of prophecy and myth. The Israelites, emerging from the crucible of desert wanderings, may have been no exception. If the burning bush was indeed an acacia releasing psychoactive fumes, then what we remember as divine command might also be remembered as humanity's continuing dance with the chemistry of the natural world. It is tempting to dismiss this as reducing the sacred to the chemical, but perhaps it is the opposite. Chemistry does not erase mystery. It explains how the natural world itself can be the source of awe. Whether or not Moses breathed in molecules of DMT, The story reminds us that ancient people did not separate the spiritual from the physical. The desert, the flame, the tree, and the vision were all one. What remains for us is the haunting possibility that some of humanity's most enduring revelations were sparked not only by faith, but also by the properties of plants rooted in the soil. If we place the story of Moses in the broader cultural landscape of the Late Bronze Age, another layer comes into view. This was a world where neighbouring peoples, from the Canaanites to the Egyptians, were deeply familiar with ritual smoke. Incense made from frankincense and myrrh was traded along vast caravan routes, prized not just for its scent but for its ability to create a boundary between ordinary life and sacred ceremony. In this context, the burning of acacia would not have been unusual. What would have set it apart was the way its smoke affected the body and mind. Unlike incense that calms or soothes, acacia could agitate, overwhelm, or transport. For a figure like Moses, leading a people through the stark emptiness of Sinai, a vision from such smoke might have been received not as personal hallucination, but as a collective sign, evidence that even in the wilderness the divine had not abandoned them. One detail in the biblical narrative often overlooked is Moses' reaction. He hides his face, afraid to look directly at the vision. This reflex of awe mixed with terror echoes countless reports from cultures where entheogens play a role. People describe their encounters as both beautiful and overwhelming, moments where the human sense of control collapses. Such accounts may suggest that the burning bush episode, whatever its literal basis, was framed by the psychological reality of an altered state. It was not simply seeing something extraordinary, but being overcome by an intensity that demanded interpretation as sacred. There is also the question of continuity. Acacia wood appears again and again in Israelite ritual prescriptions. The Ark of the Covenant, the holiest object of the wandering tribes, is said to have been built of acacia. Altars were to be constructed from it. This could be a matter of practical availability, acacia was common in the desert, but it may also reflect an inherited awareness of its unusual qualities. If the first encounter with God had been mediated through the burning of such wood, later generations may have preserved its use in sancta as a way of maintaining that link. The tree itself became a reminder of encounter, a living material memory. To approach this story as historians or scientists is not to drain it of meaning. It is to consider how human experience, biology and ecology shape even our most enduring myths. If Moses' vision was sparked by the chemistry of a desert plant, then it joins a long line of moments where nature's molecules helped script the sacred. And if it was not, if it was simply metaphor or miracle, the fact remains that humans told it in terms of fire, smoke and a bush that burned without consuming, a language rooted in what the senses know. The mystery of Sinai remains, but perhaps it is less about separating divine from human than about recognizing how deeply entwined the two have always been. How many gods were born in smoke, in spores, or in cups filled just a little too generously? Across the long centuries of antiquity and the medieval world, faith was rarely a sober affair. The great religions of the Old World, whether Jewish, Christian, or Islamic, all wrestled with the same paradox. Substances that could dissolve fear and awaken ecstasy also threatened to blur discipline, hierarchy, and law. What we often forget is that what counted as sacred ritual and what counted as dangerous intoxication was not a fixed rule handed down from above, but a shifting negotiation between leaders, communities, and the substances themselves. In Judaism, there is a curious tension between celebration and prohibition. Wine is not just permitted but commanded in certain rituals. The Sabbath begins with a blessing over it, and weddings and Passover seders unfold with its taste on the tongue. Yet alongside this affirmation is the story of Nadab and Abihu, the sons of Aaron, who were struck down for bringing strange fire into the tabernacle, an episode many interpreters link to intoxication. This duality appears again in the Festival of Purim, a holiday rooted in survival against annihilation, where celebrants are told to drink until they cannot distinguish between blessing Mordecai and cursing Haman. Such prescriptions are more than curiosities. They reveal a recognition that altered states, whether through alcohol or perhaps other substances, could blur moral distinctions in ways both dangerous and strangely holy. Christianity inherited and transformed this ambiguity. From its earliest days, the Eucharist, the breaking of bread and the sharing of wine, stood at the centre of its worship. The wine was not a casual drink, but a sacrament, a symbol of divine blood, a mystery that made the intoxicating cup into the holiest object imaginable. Yet this sacred embrace carried anxiety. To drink too much or outside the ritual frame threatened scandal. The letters of Paul already warn against drunkenness in Christian gatherings. Over the centuries, councils and theologians refined boundaries. Wine as Christ's blood was sacred, wine at a feast was permissible, but wine as personal excess was condemned. The paradox was inescapable. The very substance that lifted hearts in church could ruin bodies in the tavern. Islam too struggled with this divide, though in a sharper key. The Quran speaks of wine first with caution, then with outright prohibition. Intoxicants may offer some benefit, but their harm is greater than their use. By the time of the Prophet's death, wine and fermented drinks were forbidden. And yet, within the folds of Islamic spirituality, intoxication found another route. The Sufis, mystics devoted to union with the divine, spoke of wine constantly, not in their cups, but in their poetry. Rumi's verses spill over with metaphors of drunkenness, of losing oneself in the tavern of God. These were not calls to literal drinking, but acknowledgments that the language of intoxication was the best way to describe the loss of self in divine love. And even here, history records rumours that some Sufi orders may have experimented with substances, hashish above all, that blurred the line between metaphor and practice. What we see across these traditions is not a neat division between sacred sobriety and profane indulgence, but a long debate about where ecstasy belongs. Ritual allowed for a controlled intoxication, the Passover wine, the Eucharistic chalice, the Sufi metaphor of the cup. Outside those boundaries, intoxication was disorderly, a threat to authority. The very same altered state could be holy in one setting and sinful in another. This double standard is less about hypocrisy than about human recognition. People knew that substances could open doors, but doors opened at the wrong time or for the wrong people could lead to chaos. Religion's task became to script when, how, and why one was allowed to drink, smoke, or ingest, and to punish those who crossed the line. In doing so, faith communities kept alive an ancient truth, that the chemistry of plants and fungi was not separate from the chemistry of belief. The gods were not born in smoke and spores, but they certainly spoke more loudly through them. One way to see the role of intoxicants in religion is to follow how language itself bent around them. Terms that once meant literal wine or smoke grew into metaphors for spiritual states. A psalm could describe the cup that overflows, not simply as abundance, but as a hint at intoxication in God's presence. Early Christian mystics extended this. To be drunk in the spirit was to be lifted beyond ordinary reason. In Sufi poetry, intoxication became almost a grammar of love, the only way to express the unspeakable. This evolution of words tells us that long after the substance itself might have been banned or restricted, its effect remained the most vivid image available to describe divine encounter. At the same time, leaders worried about control. Rulers and priests knew that substances could dissolve social order as easily as they dissolved personal inhibition. The rabbis of late antiquity set strict guidelines on when and how wine could be blessed, determined not only by piety, but by the fear of disorder. Church councils in the Middle Ages treated drunkenness among clergy as scandalous, a danger to authority itself. Islamic jurists debated endlessly over what counted as an intoxicant. Was fermented honey wine included? What about opium? The principle was simple. Anything that clouded judgment was forbidden. Yet behind these rulings lay the acknowledgement that people kept seeking these experiences regardless of law. We also see a fascinating tension between elite and popular practice. In cities, officials might strictly enforce prohibitions, while in rural areas, people continued long traditions of folk medicine and ritual involving plants, brews, or smokes. Archaeological finds from the Levant and North Africa reveal traces of cannabis, henbane, and opium in ritual contexts, sometimes in graves, sometimes in vessels found near altars. These discoveries remind us that what theologians wrote and what ordinary communities practiced were not always the same. religion as lived experience was often messier, less consistent, and more open to intoxication than the official texts admit. The medieval period also introduced new substances into the mix. The spread of coffee from Ethiopia and Yemen into the wider Islamic world transformed worship and devotion. Here was a stimulant, not an intoxicant, yet its effects on alertness and mood stirred debates remarkably similar to those about wine centuries earlier. Some Sufis embraced it as a gift that kept them awake during night prayers. Others condemned it as suspicious, too close to intoxication. This shows that the boundary between sacred aid and forbidden drug was always porous, shaped less by chemistry than by culture. By tracing these debates, we are reminded that religion has never been separate from the chemical realities of human life. From acacia smoke to Eucharistic wine to Sufi coffee circles, substances have shaped how people reach toward the sacred. The question was never simply whether to partake, but under whose authority, in what setting, and with what meaning. In this tension, gods were imagined, rituals solidified, and communities defined. Imagine the glittering palaces of Bronze Age Crete, their walls painted with dolphins and lilies, their storerooms packed with jars of oil and wine, their harbours busy with ships sailing east to Egypt, west toward Italy, and north into the Aegean. We tend to picture the Minoans, as archaeologists later called them, as a people of art and trade, the first high culture of Europe. But buried within this vision is a stranger suggestion, that some of their wealth, and perhaps their influence, was built on the most ancient drug trade of the continent. Among the finds from Crete are tiny vessels shaped like poppy heads, vessels that likely once held a thickened form of opium mixed with olive oil. This blend, researchers argue, could be drunk, poured, or rubbed into the skin, a Bronze Age narcotic with both medicinal and intoxicating potential. Opium itself comes from the sap of the opium poppy, a plant native to the Mediterranean that flourishes under the hot summers and mild winters of Crete. Farmers learned that when the seed pods were cut and the milky latex dried, it produced a substance that dulled pain, calmed nerves, and carried people into a drowsy, dreamlike state. By the second millennium before the Common Era, poppy cultivation in Crete seems to have been more than a domestic affair. Archaeological traces suggest that the Minoans may have developed a specialty in preparing and exporting this substance, blending it with olive oil to make it easier to transport. In a world before refrigeration and before distillation as we know it, such an innovation would have made opium more stable and more marketable across long sea voyages. This is not simply speculation. Some of the poppy-shaped vessels excavated from Cretan sites still bear chemical residues consistent with opium. Their stylized design, mimicking the swollen capsule of the poppy, is itself a kind of branding, a Bronze Age logo. To hold such a vessel was to know what it contained. And while opium might have been used locally for ritual, goddess figurines from Crete are sometimes crowned with poppy pods, it is hard to ignore the maritime networks of the Minoans. Their ships connected Crete to cultures that prized exotic goods, especially substances with both medical and mystical value. To offer opium alongside olive oil and wine was to sell not just nutrition but escape, relief, and vision. This raises the larger question of how deeply drugs were embedded in the story of Europe's first palatial society. The Minoans left no written texts we can fully read. Their linear script remains undeciphered, so we cannot know what words they used for poppy or opium, but their art and artifacts suggest they saw the plant not as ordinary but as divine. The so-called poppy goddess figurinas with their uplifted arms and crown of seed pods seem to link the substance directly to fertility, life, and perhaps even death. If the goddess herself wore the symbol of the drug, then opium was more than commerce. It was cosmology, and yet commerce mattered. The Minoans' rise coincided with an era of expanding long-distance exchange. Tin from as far as Britain, gold from Egypt, lapis from Afghanistan. Goods moved astonishing distances. If opium flowed through these same channels, Crete's harbours may have served as the first European nodes in a trade of intoxication that would never quite disappear. In this sense, the Minoans were not just builders of palaces and painters of murals. They were quite possibly the first drug dealers of Europe, supplying a commodity as desirable as any metal or gem. To be clear, we cannot prove the scale of this trade. Archaeology gives us fragments, a residue here, a vessel there, a figurine crowned with poppies, but the pattern is difficult to ignore. Pain relief, ritual ecstasy, and the economic logic of seaborne trade all converged on the poppy. Whether consumed by farmers on Crete, worshippers in shrines, or elites in foreign courts, opium may have shaped the experience of the Bronze Age in ways we're only beginning to imagine. What we do know is that by the time later Greeks looked back, they already associated Crete with both gods and mysteries. Perhaps part of that memory was seeded in fields of poppies, harvested in silence and shipped across the sea. The possibility of a Bronze Age drug economy on Crete also gains weight when we place it alongside other evidence of how Minoan society was organised. These were people who mastered storage and distribution on an unprecedented scale. Archaeologists working at Knossos, Phaistos and other palatial centres have uncovered vast magazines lined with pithoi, the giant jars that once held grain, wine and oil. This was not casual stockpiling but centralised control. Palaces acted like warehouses and redistribution hubs, taking in harvest from farmers and sending them back out in measured portions. If opium-infused oil was part of this system, it could have been carefully rationed or exported in the same way as olive oil itself. Such management would have made the difference between a scattered folk remedy and a commodity with a regional significance. We also have to remember that the Minoans were not isolated experimenters. Across the eastern Mediterranean in this period, societies were already familiar with psychoactive plants. Egyptian texts mention the use of mandrake, blue lotus, and henbane for ritual and medicine. In Mesopotamia, clay tablets record recipes that mix herbs with beer or wine for altered states. Crete sat at the crossroads of these civilizations, and it would have been astonishing if the island's merchants had not noticed the demand for substances that could soothe pain or open the mind. The sea was not a barrier, but a highway, and on that highway, intoxicants were as marketable as metals. Even the collapse of the Minoan world in the 15th century before the Common Era carries a curious echo of this trade. Some scholars argue that natural disasters, earthquakes, and volcanic eruptions destabilized the island. Others point to shifts in trade routes, as mainland powers like Mycenae took over maritime dominance. If opium had indeed been one of Crete's specialties, then losing control of those sea lanes would have undercut their economic base as much as any earthquake. Drugs have always been entangled with geopolitics, and here in the Bronze Age we might see one of the first examples. What fascinates us today is not just the suggestion of an ancient narcotic economy, but the way it complicates our view of civilization. The Minoans are often described as Europe's first high culture, admired for their art, architecture and maritime skill. To add opium to that picture does not diminish their sophistication. It reminds us that what we call civilization has always been built on complex relationships with plants, with pain relief, with ecstasy. The story of Crete, told through poppy-shaped vessels and residues in clay, is another chapter in humanity's long negotiation with the substances that alter perception. Whether as sacrament, medicine or trade good, the poppy was part of the foundation on which the Minoans built their palaces and launched their ships. What if the very first monumental structure humans ever built was not a fortress, not a palace, and not even a temple in the sense we usually imagine, but something closer to a gathering ground, a place to eat, drink, and blur the edges of ordinary life together? On a hill in southeastern Turkey, buried under layers of soil and forgotten for millennia, lies Gobekli Tepe, a site more than 12,000 years old. Its towering limestone pillars are carved with foxes, vultures, snakes, and abstract signs that still puzzle us. Archaeologists once assumed that monumental architecture emerged only after farming, but here the order seems reversed. Hunters and foragers, still living without crops or herds, carved and hauled stones weighing tons, arranging them into circles that could hold dozens of people. What would drive them to such effort? One compelling answer is that Gobekli Tepe was humanity's first great party place. Excavations at the site reveal not only the pillars and enclosures, but also traces of feasting. Tens of thousands of animal bones, mostly gazelle, aurochs, and wild game, are scattered across the layers. These were not casual meals of a few families but large gatherings of many groups. Archaeologists believed that the site drew people from across the region, clans who may have only occasionally met but who needed to exchange news, partners, and stories. Feasting, and possibly drinking, would have made these meetings more than transactions. They were celebrations of belonging, events that tied scattered foraging bands into a wider community. The hint of beer hovers at the edges of the site's story. Stone basins, some large enough to hold dozens of litres, have been found nearby, their interiors showing residues of calcium oxalate, a telltale byproduct of brewing. At a time when farming had not yet been firmly established, wild grains were already being collected, ground, and transformed into something that foamed and intoxicated. If beer was indeed brewed here, it may have been among the earliest examples in the world. And it reframes the question of what pushed humans toward cultivation. Perhaps it was not bread that first motivated planting, but beer. A patch of barley or wheat meant not only calories, but the possibility of turning gatherings into revels, of sustaining ritual and alliance through intoxication. What makes Gobekli Tepe particularly striking is the absence of domestic structures. People did not live there. They came, feasted, and left. This separation hints at a site devoted purely to ritual and social performance. The carved animals might not have been deities in the later sense, but symbols of clans, totems that anchored identity in the shared space. To gather around the pillars, under the watchful carvings of predators and birds, would have been to step into a world apart, a circle of meaning. Add the possibility of drink, of wild grain brewed into an intoxicant, and the circle becomes a stage for altered states, for binding strangers into kin, for managing the problem that haunts every small population: inbreeding. By gathering at places like this, exchanging partners, and forging ties, human groups could maintain genetic diversity while also affirming cultural bonds. To call it a nightclub is tongue-in-cheek, but the comparison is not absurd. It was a place where music, dance, food, and perhaps alcohol converged to suspend the ordinary. Unlike later temples built for priests and kings, Gobekli Tepe belonged to a world without palaces. Its pillars were raised by people who still roamed with animals, who carved stone not to guard property, but to create a shared theatre of memory and emotion. We cannot know exactly what was felt there 12,000 years ago, but the traces suggest awe, intoxication, and community, woven together in ways that would shape the trajectory of human culture for millennia to come. The enigma of Gobekli Tepe is not only in its carved stones, but in its timing. 12,000 years ago, the world was emerging from the last glacial maximum. The climate was warming, ice was retreating, and grasslands were spreading where glaciers had once loomed. Human groups were still foragers, but their numbers were growing, and so were their interactions. Sites like Gobekli Tepe seem to crystallize this moment, when small-scale societies began to experiment with scale. Bigger gatherings, bigger monuments, and bigger ideas. The carved enclosures, some 20 metres across, would have required coordination far beyond the daily needs of a foraging band. It suggests that even before agriculture, people were practicing the skills of large-scale cooperation, organising labour, planning logistics, and sustaining collective vision. One way to draw people into such coordinated efforts is through shared celebration. Archaeologists studying the site note that feasting, by its very nature, is an effective social technology. A communal meal requires contributions, creates obligation, and redistributes resources in a way that strengthens ties. The bones found at Gobekli Tepe were not just discarded scraps, but the remains of large-scale butchering and roasting events, many animals killed and consumed together. Such spectacles would have created memories powerful enough to bring people back season after season, a cycle of pilgrimage reinforced by expectation and ritual. The introduction of alcohol into this dynamic magnifies its potential. Even if the evidence for beer brewing at Gobekli Tepe is still debated, the discovery of fermentation residues suggests at least some experimentation with grain beyond simple eating. Fermentation transforms food into something unpredictable. The warmth of alcohol, the altered perception, the collective euphoria. These qualities make drink more than a caloric supplement. They make it a cultural tool, capable of dissolving barriers, easing negotiation, and amplifying emotion. For groups that needed to forge alliances and marriages across distance, Alcohol could grease the wheels of cooperation in ways as effective as shared bloodlines or mutual defence. The symbolic carvings at the site also raise questions about how intoxication may have been linked with meaning-making. Foxes, boars and vultures etched into stone may have been emblems of myth, clan identities, or reminders of the natural world from which all life depended. Standing in the stone circle, drinking a fermented brew, participants may have felt themselves in conversation with these animal guardians, weaving stories that frame their gatherings in sacred language. While we cannot know the content of those myths, the carvings suggest a merging of the practical, food, drink, marriage networks, with the imaginative and ritual. In this light, Gobekli Tepe can be seen as one of the earliest experiments in turning sustenance into spectacle and survival into ceremony. It was not yet a city, nor a farmstead, but something in between. A site where humans rehearsed being more than scattered bands, where they tested the potential of coming together in large numbers, and where altered states, whether through music, dance or drink, provided the glue to hold it all. Perhaps that is why the builders eventually buried their creation under tons of earth. Having served its purpose, it was time to move on. But the memory of gathering, feasting and possibly drinking at the hill would echo into the agricultural and urban worlds that followed. What if the first hierarchies of power, the first priests and kings, were not built on swords, but on barley? Around 5,000 years ago in Mesopotamia, the land between the Tigris and Euphrates, humans were learning what it meant to live in cities for the very first time. Urban life was a radical experiment. Populations were growing far beyond the size of a band or village, and strangers had to find ways to cooperate. Food was the foundation of that experiment, and beer became its most persuasive instrument. Archaeologists have long puzzled over why the first farmers went to the trouble of cultivating cereal grains. Bread is one answer, beer may have been the other. Fermentation turned barley and emmer wheat into a liquid food that was easier to store, safer to drink than water, and importantly intoxicating. Beer nourished and delighted, but it also demanded management. Grain had to be collected, stored and allocated to produce it. Once that system existed, it was easy to imagine how control of beer became control of people. In the Sumerian city of Uruk, tablets etched in cuneiform, the world's earliest writing, record the allocation of barley and beer rations to workers. These were not casual drinks passed around a campfire, they were wages. A jar of beer was payment for hauling bricks, for tending canals, for serving the temple. The act of receiving your ration tied you to the institution that provided it, whether temple or palace. In this way, beer was no longer just a byproduct of grain. It was a currency. With currency comes accounting, and with accounting comes hierarchy. Those who managed the storehouses and controlled the flow of beer acquired authority that was more binding than brute force. They became priests, then kings, and eventually both. The symbolic power of beer was equally potent. Temples were not only warehouses but ritual centres, and beer flowed in ceremonies to the gods. Offerings were poured out to deities like Ninkasi, a goddess specifically associated with brewing. To drink beer was not just to quench thirst, but to participate in a cosmic transaction. The frothy liquid that lifted spirits in a tavern also legitimised the authority of those who claimed to act on behalf of divine order. Kingship in this light can be seen as fermented as much as it was forged. Rulers positioned themselves as intermediaries who guaranteed the flow of life-giving drink. Without their system, the grain would spoil, the vats would be empty, and society would collapse. Evidence from residues found in ancient jars confirms that beer was thick, cloudy, and consumed communally, often through long straws so that multiple people could drink from a single vessel. These gatherings were not merely social. They rehearsed the structure of society itself, many dependent mouths converging on a resource administered by the few. A simple act, sharing a pot of beer, mirrored and reinforced a new world of stratification. We cannot know if the first Sumerian labourer, sipping through a reed, thought of their drink as a wage, a gift, or a chain. But we can see in the clay tablets and temple walls how intoxicants shaped the very architecture of inequality. From a humble grain, the logic of surplus, storage and control fermented into something larger than sustenance. Beer became a foundation of organised religion, an axis of state power, and perhaps the most persuasive reminder that civilization is as much about what we drink as what we build. The irony is that this invention, which bound communities together, also introduced dependence. To drink was to acknowledge the system. To thirst was to need the king. If hierarchy has a taste, perhaps in ancient Mesopotamia it was the taste of barley, sweetened by fermentation and sanctified by ritual. The spread of beer across Sumerian society also reshaped daily life in quieter ways that are easy to overlook. Taverns, for example, appear in cuneiform texts, not only as places of merriment but also as nodes of social negotiation. These were the establishments often run by women, where travellers could stop for a drink, strike deals, or exchange information. In a world where writing was still limited to scribes and elites, the tavern was a kind of oral archive, a place where news and stories moved faster than clay tablets. That beer facilitated these exchanges is telling. It was not merely a background substance, but the very medium in which information and community were brewed. At the same time, beer anchored the rhythms of labour. Canal digging, brick-making and harvest work were gruelling under the Mesopotamian sun. Payment in beer did more than compensate hunger and thirst. It softened the hardship, transformed fatigue into camaraderie, and ensured that labourers associated their effort with immediate reward. This emotional leverage cannot be underestimated. Control of grain silos may have built the foundation of state power, but the warm buzz of a rationed beer each day kept the system tolerable. Elites were not naive to this dynamic. By offering sustenance laced with pleasure, they maintained loyalty without constant coercion. There is also evidence that beer became an important part of diplomacy. When city-states met to negotiate alliances or end conflicts, the sharing of drink was often central to the ritual. The act of raising a vessel together sealed agreements in ways words alone could not. Archaeological finds of standardized drinking vessels suggest that both the quantity and the ritual of consumption were codified, creating expectations that bound participants to their promises. To betray an agreement after sharing beer with another ruler may have been seen as not just a political offence but a sacrilege. The material remains further illuminate how beer was embedded in Sumerian cosmology. Residues in religious vessels, often buried in temple context, point to offerings poured not for human consumption, but for divine ones. The gods were imagined as partaking in the same intoxicant as mortals, a liquid thread weaving heaven and earth together. By positioning themselves as mediators of this divine drink, kings and priests magnified their legitimacy. The state was not just feeding workers, it was feeding the cosmos. When we step back, what emerges is a picture of beer as both tool and symbol. It fueled labour, lubricated diplomacy, affirmed ritual, and cemented hierarchy. Its pervasiveness shows that civilization was not engineered by abstract principles alone, but by substances with immediate visceral effects. People needed calories, yes, but they also needed connection, relief, and meaning. Beer delivered all of these, binding society to the temple and the palace. That we can trace so much of early urban life through the residues of barley and yeast is a reminder that the building blocks of history are not always stone or bronze. Sometimes they are bubbles rising in a clay jar, fragile yet foundational. By the 16th century, Europe was changing faster than it ever had before. Printing presses were spreading ideas, Protestant reformers were challenging Catholic authority, and merchants were binding distant cities together with trade. Yet amid all this upheaval, a quieter shift was brewing in taverns and kitchens. The transformation of beer itself. For centuries, European beers had been flavoured with druit, an herbal mix that could include yarrow, mugwort, heather, juniper, henbane, and sometimes even more dangerous or hallucinogenic plants. These were not just flavourings, but pharmacological cocktails, with effects ranging from mild sedation to outright visions. Brewing was often a household practice tied to women's work, and the line between alewife, healer and herbalist was sometimes indistinguishable. But by the early 1600s, a new set of rules was imposed that narrowed what beer could be and what culture was allowed to drink. In Germany, the famous Reinheitsgebot, or beer purity law, was passed in 1516. On its face, the law looked practical. It limited beer to only 3 ingredients: water, barley and hops. The stated purpose was to ensure consistent quality, to keep prices stable, and to reserve wheat for bread rather than brewing. But underneath these economic reasons lay another transformation. By outlawing the use of Groot, the law effectively ended the centuries-long tradition of spiced, herbal, and occasionally hallucinogenic ales. With the stroke of a legal pen, entire categories of altered experience were excised from daily life. Why? Part of the reason was control. Groot had been managed through local monopolies, often linked to church authorities, who taxed and regulated the herbal blends. By shifting to hops, which could be cultivated at scale and standardized, brewing was wrested away from small producers and concentrated in larger commercial hands. It was no coincidence that this also displaced many women from brewing, rebranding it as a male-dominated profession tied to guilds and city regulations. The law thus reflected not only an economic shift, but a cultural one, where the church and state could more tightly regulate what people consumed and how they experienced intoxication. Another reason was suspicion. Many of the plants used in Groot, like henbane or mandrake, were associated with witchcraft in medieval imagination. Their effects could be disorienting, erotic, or hallucinatory, and as religious authorities tried to draw firm lines between acceptable piety and dangerous heresy, these brews became suspect. To drink hopped beer was safe, lawful, and orthodox. To drink Groot was to flirt with the forbidden. In witch trials of the era, women accused of brewing flying ointments or strange concoctions were often tied to the old herbal traditions. By enforcing hops as the sole legal flavouring, authorities could extinguish not only unregulated commerce but also the folk pharmacology that linked beer to visionary or mystical states. The irony is that hops themselves were psychoactive, but in a very different direction. Unlike the stimulating or hallucinogenic qualities of herbs and Groot, hops are sedative. They calm, they relax, they promote sleep. A hopped beer is less likely to send its drinker into ecstatic visions, and more likely to quiet them into compliant drowsiness. In this sense, the purity law can be read not only as an economic regulation, but as a cultural taming of intoxication. Beer was domesticated, its wild edge dulled, its capacity to disturb or inspire visions clipped back. What had once been a space of herbal experimentation became a standardized, taxable, and subdued commodity. This was not the end of beer's social role. It remained central to European diets and identities, but it marked the death of one kind of cultural intoxication. The buzzing, unpredictable, often feminine-coded brews of the medieval period gave way to a more docile drink, aligned with authority. By purging the old ingredients, Europe may have lost more than flavours. It may have lost a line of continuity with the ecstatic and visionary uses of plants that stretch back to prehistory. And so, a law about barley and hops tells us as much about power and belief as it does about taste. The purity law did not remain a local German curiosity. Over time, it spread its influence outward, shaping the wider brewing culture of Europe and eventually the world. In Bavaria, where it was first enforced, the law became a matter of pride and identity. Brewers boasted that their beer was pure, untainted by suspicious plants or questionable additives. This branding worked remarkably well, creating a cultural link between hops, order, and quality. What had started as an economic and social regulation turned into a moral one. To drink beer brewed outside the law was not just risky but vaguely improper. The knock-on effects were significant. Local traditions that had once been richly diverse, beers flavoured with bog myrtle in Scandinavia or with rosemary and sage in the Low Countries, were marginalised. Many of these traditions survived in small pockets or resurfaced much later in the craft beer movement of the late 20th century, but for centuries they were pushed to the edges. The diversity of flavours collapsed into a narrower spectrum, dominated by the sharp, resinous bite of hops. What Europe gained in stability and standardisation, it lost in variety and experimentation. The gender shift was equally lasting. Brewing, once tied to household economies and carried out by women known as alewives, became increasingly commercial and male-dominated. With hops requiring larger infrastructure for cultivation and preservation, brewing aligned itself with guilds and cities. The alewife, with her herbal knowledge, who may have carried recipes from grandmother to granddaughter, now appeared suspect. Some scholars have even noted that the stereotypical image of the witch, pointed hat, cauldron, broom, may have roots in the iconography of medieval alewives advertising their brews. Once the purity law and related regulations undermined women's role in brewing, that association turned from familiar to dangerous, from everyday to diabolical. The broader context was Europe's uneasy relationship with intoxication. Authorities did not seek to ban alcohol outright. It was too central to diet and ritual, but they wanted it domesticated, manageable, predictable. Beer became the acceptable intoxicant precisely because it had been stripped of the visionary elements that once linked it to shamanism, herbalism, or even sorcery. In that sense, the purity law marks a pivot from a Europe that tolerated altered states as part of the cycle of life to a Europe that treated them with fear. The same centuries that saw beer regulated in this way also saw the Inquisition, the witch hunts, and the Reformation's battles over religious orthodoxy. And yet, even in this controlled form, the memory of those older brews lingered. Folklore preserved whispers of magical drinks, flying ointments, or ales that brought dreams. The law may have tamed beer, but it could not erase the long memory of humanity's relationship with plants that alter the mind. In some ways, the purity law is a testament to how powerful those older traditions were, powerful enough to be feared, outlawed, and remembered. What if the whole question has been the wrong way around? For decades, the stoned ape idea has asked whether psychedelic plants and fungi somehow sculpted the human mind into what it is today. It is a captivating suggestion, one that thrives in late-night conversations and speculative books, and one that stubbornly lingers because it feels like it explains too much to ignore. But when we place it under the light of science, the evidence is never more than circumstantial. We can map the savannahs and dung trails where mushrooms sprouted. We can document the chemical realities of psilocybin and DMT. We can point to the cave art and the shamanic rituals and the biblical visions. Yet, when we ask whether these things caused us to become human, the answer dissolves into the larger mystery of why we became human at all. It is here, at the end of our long story, that humility matters most. Psychedelics clearly played a role in shaping cultures, binding groups and inspiring rituals across continents and millennia. They offered glimpses beyond the ordinary, and humans again and again wove those glimpses into meaning. But the leap from cultural catalyst to evolutionary engine is too far for the data to carry. What we can say is simpler. Our species has always sought the strange. Whether through fermented fruit, smoke curling in ritual fires, or bitter-tasting mushrooms, we have leaned toward the threshold between ordinary perception and something other. That tendency is not proof that psychedelics created humanity, but it does suggest they reminded us of just how pliable the human experience can be, and perhaps that is the more profound insight. To be human has never meant to walk a single sober line. It has meant to test boundaries, to tinker with diets, to experiment with plants, to build myths from sensations we cannot quite name. Some experiments gave us nutrition, some gave us poison, and some gave us visions that outlasted the night. Our evolutionary story is full of accidents and detours, and psychedelics, if nothing else, are part of that landscape of chance. They remind us that becoming human was not a straight march of progress, but a series of encounters with the unexpected. So did mushrooms and smoke and brews make us who we are? The best we can say is that they walked alongside us. They were never the sole driver, but they were companions in the long process of self-discovery. They gave us metaphors for the divine, for death, for rebirth, for the strange capacity of a brain to see more than what is directly in front of it. They helped us craft stories that outlived bones and stone tools, and in that sense, whether they were ever engines of evolution or not, they became part of what we call humanity. As we close this journey, one truth stands above the speculation. The human story is inseparable from curiosity. We were always going to taste what we should not, to inhale what burned, to drink what frothed, to chew what glowed. And sometimes those experiments gave us glimpses that were terrifying, sometimes healing, and sometimes just strange. That is not proof of the stoned ape, but it is proof of something else, that being human has always meant living on the edge of the known, playing with the unknown, and carrying those stories forward. There is also another way to think about the question, one that does not require proof in the form of fossils or DNA, but instead rests on the continuity of human behaviour. If we look across cultures and centuries, we find the same repeated impulse. People seeking out altered states not as a distraction, but as a means of orientation. It might be tempting to dismiss such pursuits as side notes in the story of survival, yet the persistence of these practices suggests they answered needs as real as food or shelter. A ritual meal with psychoactive plants could mark transitions, ease grief, or bind a scattered group into a common rhythm. Even when stripped of evolutionary speculation, this alone shows that psychedelics have had a durable place in what it has meant to live as a human. Still, we cannot forget that speculation has its limits. Evolutionary history is written in fragmentary fossils, incomplete archaeological layers, and molecules of DNA that rarely survive the passage of tens of thousands of years. No psilocybin molecule has been pulled intact from a site 2 million years old. No cave painting comes with a label that reads, "Made while tripping." What we have are hints and patterns, and it is responsible to admit that these can only ever support stories, not prove them. This is why so many scientists, when asked whether drugs made us human, smile, shrug, and redirect the conversation toward what the evidence can actually show. And yet, to reduce the question only to hard data is also to miss something important. Human history has always been lived at the intersection of biology and imagination. We know that fire did not just warm our bodies, but transformed our diets and our nights. We know that stone tools did not just cut meat, but also reshaped hands, coordination, and social structures. Psychedelics belong to this same category of catalysts. Even if they did not spark new genes or brain structures, they changed what people did together, what they feared, what they told their children. They gave metaphors for crossing thresholds, for dying and being reborn, for touching the divine. That is not evolutionary biology in the strict sense, but it is cultural evolution, and culture has always been one of humanity's most powerful adaptations. So perhaps the question is not whether mushrooms or smoke or brews made us human, but whether they revealed what was already waiting in us. A nervous system tuned for curiosity, a mind eager to make meaning, a species restless enough to test the borders of ordinary life. In that sense, psychedelics did not invent humanity, but they may have amplified one of its oldest instincts, to wonder at what lies just beyond the edge of the firelight. Thank you, fellow sapiens, for wandering this timeline with me, for drifting into deep time, for slowing down and remembering. If this helped you fall asleep, helped you study, or simply helped you step out of the noise for a while, thank you for being here. If you think more people should know this story, you know what to do. Like, subscribe, share it with the sapiens in your life, and tell me, are you listening before bed, while working, or somewhere in the world I can only imagine? And as always, stay curious, stay calm. I'll see you in the next story.